Apple wants China's RAM after a 98% price surge. MacBooks already cost more. Apple has spent decades building one of the strongest supply chains in technology. But this time, even Apple could not absorb the pressure. MacBook and iPad prices have already increased after the cost of memory and storage chips surged across the industry. Now Apple is reportedly asking Washington for political clearance to purchase DRAM from Changshin Memory Technologies, better known as CXMT, China's largest memory chip producer. The reported request does not mean a deal has been signed. It does not mean Chinese RAM is already inside new MacBooks. And it does not mean CXMT has replaced Samsung, SK Hynix, or Micron. But the fact that Apple is even considering this option reveals how extreme the memory shortage has become. DRAM prices reportedly rose by as much as 98% during the first quarter of 2026, with another sharp increase expected during the second quarter. The AI boom is consuming advanced memory, manufacturing capacity, packaging resources, and capital at a pace the consumer electronics industry did not expect. Why Apple raised prices? Apple normally avoids sudden price changes during a product cycle. The company prefers predictable pricing because customers compare models, retailers plan inventory, and the entire product lineup is carefully positioned around specific price points. That strategy changed when memory and storage costs climbed too quickly. The entry MacBook Neo rose from $599 to $699. A 512GB MacBook Air increased from $1,099 to $1,999. The 128GB iPad Air moved from $599 to $749. Other Mac, iPad, HomePod, and Apple TV products also became more expensive. Apple said the increases were unavoidable because the company could no longer protect customers from the speed and scale of the component cost surge. If Apple cannot fully contain memory inflation, smaller computer and smartphone manufacturers are likely facing even greater pressure. How AI created a memory shock. An AI accelerator is only as useful as the memory feeding it. Large models require enormous quantities of data to remain close to the processor. Training needs high bandwidth memory to keep thousands of computing units active. Inference also consumes memory because model weights must be read repeatedly while each new token is generated. This has made HBM one of the most valuable products in the semiconductor industry. Samsung, SK Hynix, and Micron are investing heavily in high-bandwidth memory because it earns stronger margins than many conventional products. It uses DRAM manufacturing technology, advanced packaging, engineering talent, capital, and factory time that might otherwise support ordinary server, laptop, or mobile memory. When capacity is limited, they prioritize the customers and products offering the highest return. AI companies can justify paying more because a single accelerator system may cost tens or hundreds of thousands of dollars. A laptop maker cannot increase component costs indefinitely without damaging demand. Prices rise. Apple's new prices are one of the clearest signs that the AI memory shortage has moved beyond server rooms. Why CXMT suddenly matters. CXMT was founded in 2016. DRAM is one of the hardest semiconductor markets to enter because success depends on scale, yield, process control, reliability, and relentless cost reduction. A small process variation can reduce the number of usable chips produced from every wafer. CXMT began by supplying more conventional DRAM products for China's domestic market. Its early technology lagged the global leaders, but it continued expanding capacity, improving processes, and introducing newer generations of DDR and low-power memory. The company is now widely regarded as the world's fourth largest DRAM supplier, although it remains far smaller than the top three. Apple does not need CXMT to be larger than Samsung. It needs another supplier capable of producing qualified memory at meaningful volume. Even a modest additional source can strengthen Apple's negotiating position and reduce dependence on a tightly concentrated supplier base. The shortage has transformed CXMT from a distant challenger into a potentially useful option. What Apple is reportedly asking for. According to reports, Apple has been lobbying the United States government for clearance to buy memory chips from CXMT. The company reportedly approached officials because CXMT appears on a Pentagon list of companies alleged to have links to China's military. That listing does not automatically create a universal legal ban on every commercial purchase. However, it creates political, reputational, and regulatory risk. A supplier that is permitted today could face tighter restrictions later. Apple could spend months qualifying a product, redesigning logistics, and negotiating contracts only to see new rules block the arrangement. That is why political clearance matters, even if the transaction is not currently prohibited in the simplest legal sense. Apple wants confidence that it will not build part of its supply chain around a supplier that Washington later prevents it from using. The administration has not publicly approved the request. Apple and CXMT have not announced a supply agreement. For now, this is an attempt to create an option, not proof that the option will be used. Apple's qualification process. Supplying Apple is not as simple as offering a low price. Memory must meet strict requirements for performance, power consumption, heat, reliability, packaging, and long-term consistency. A chip may pass one laboratory test and still fail to qualify for mass production. Apple needs components that behave predictably across millions of devices. The supplier must maintain quality from one production batch to the next. It must provide enough volume on schedule. It must support Apple through product launches, regional demand changes, and unexpected factory disruptions. For MacBooks and iPads, power efficiency is especially important. Poor memory efficiency reduces battery life and creates additional heat. Reliability is equally important because defective memory can cause crashes, data corruption, or complete device failure. CXMT would need to prove that its products satisfy Apple's technical standards and that its factories can maintain those standards at scale. Apple may also require extensive audits, traceability, security controls, and contingency plans. Political permission would only open the door. Technical qualification would decide whether CXMT could walk through it. Why Samsung, SK Hynix, and Micron should pay attention. The established suppliers still dominate global DRAM. They possess larger factories, more advanced products, stronger customer relationships, and decades of manufacturing experience. CXMT does not threaten to replace them overnight. But Apple's interest would still carry major symbolic weight. Apple is one of the most demanding and visible electronics companies in the world. If CXMT qualified for even part of Apple's memory supply, other manufacturers would pay attention. A successful Apple contract could validate CXMT's reliability and production discipline. It could also give Apple more leverage during negotiations with current suppliers. Memory is a cyclical commodity business. Small changes in supply and demand can produce large price movements. Adding another credible supplier does not need to eliminate Samsung or Micron to affect the market. It only needs to weaken the assumption that buyers have no alternative. The possibility of CXMT entering Apple's supply chain could therefore influence pricing even before large shipments begin. Why China could benefit? For China, an Apple contract would be more than a commercial sale. It would demonstrate that a domestic memory producer had reached standards acceptable to one of the world's most influential device makers. That could strengthen confidence among Chinese computer, smartphone, server, and automotive companies. It could support CXMT's expansion and help the company improve through larger production volumes. Semiconductor manufacturing often becomes more competitive through repetition. Higher volume generates more process data. More data helps engineers find defects, improve yield, and lower cost. A major customer can therefore accelerate a supplier's development, but the relationship would also create dependence. CXMT would need to satisfy Apple's requirements, absorb pricing pressure, and invest heavily to support future products. Apple is famous for demanding lower costs while maintaining strict quality. Winning the business would be prestigious. Keeping it profitable would be another challenge. Could Chinese RAM lower MacBook prices? Possibly, but not immediately. Adding a supplier can improve competition and reduce procurement risk. If CXMT offers qualified memory at a lower price, Apple could reduce some of the pressure created by the shortage. However, Apple has already raised retail prices. Companies rarely reverse broad price increases quickly unless market conditions change dramatically. The memory market also remains tight. One supplier cannot instantly replace capacity across the industry. CXMT must serve domestic customers while expanding production and improving technology. Any Apple agreement would likely begin with limited volumes or selected products rather than the entire Mac lineup. There is also no guarantee that lower component costs would be fully passed to consumers. Apple could use savings to protect margins, invest in supply security, or avoid additional price increases. The most realistic short-term benefit would be preventing the situation from becoming worse. CXMT could give Apple another source of supply while the company waits for global memory capacity to catch up with AI demand. The political problem. This is where the technology story becomes complicated. Some American lawmakers are likely to oppose any arrangement with CXMT because of national security concerns and broader efforts to reduce dependence on Chinese technology. They may argue that allowing Apple to become a major customer would strengthen a strategic Chinese semiconductor company. Others may focus on supply chain resilience and consumer prices. Blocking an available supplier during a severe shortage could increase costs for American companies and customers. Apple must navigate both arguments. The company sells heavily in China, manufactures much of its hardware through Asian supply chains, and depends on global suppliers. At the same time, it is one of the most prominent American corporations and faces intense political scrutiny. A memory contract that looks economically sensible could still become politically impossible. That uncertainty may be the greatest obstacle. The honest catch. The headline is powerful, but several facts must remain separate. Apple reportedly wants clearance to buy from CXMT. Apple has not confirmed a signed contract. CXMT memory is not confirmed inside current MacBooks. The reported 98% increase refers to market pricing during a specific period, not the exact cost increase of every memory chip Apple buys. MacBook and iPad prices rose for multiple configurations, but iPhone prices had not yet increased at the time of the announcement. CXMT also remains behind the leading suppliers in advanced memory technology and total production scale. The story is not that Apple has abandoned Samsung, SK Hynix, and Micron. The story is that the shortage has become severe enough for Apple to explore a politically risky supplier it previously did not rely on. My take is that Apple's reported request is one of the clearest signs that AI has changed the value of memory. For years, DRAM was treated as a replaceable commodity purchased from a small group of established suppliers. Now memory is becoming strategic. AI companies are absorbing supply. Prices are rising fast enough to change retail products, and a Chinese manufacturer that once looked peripheral suddenly has leverage because it can add capacity. Apple may never complete the deal. Political pressure could stop it. CXMT could fail qualification. The shortage could ease before large shipments begin. But the request itself matters. It shows that supply security can be engineering decisions reshaping technology. Because Apple is not turning to Chinese memory out of curiosity. It is considering it because a 98% price surge has made the old supply chain too expensive to ignore. A laboratory in Oregon takes one of Huawei's newest smartphone processors and begins removing it layer by layer. The package comes apart. The memory is separated. The silicon is polished until structures invisible to the human eye become visible under powerful microscopes. And deep inside the chip, researchers find a number that appears to break the normal hierarchy of semiconductor manufacturing. 32.5 nanometers. That is the measured pitch of the lowest local metal layer inside Huawei's Kirin 9030 processor, manufactured by China's SEMIC using its N+3 process. Now compare that with Intel's newest commercial manufacturing technology. Inside Panther Lake processors built on Intel 18A, the equivalent layer is reportedly spaced at 36 nanometers. On that one measurement, China's 7-nanometer class process went smaller than the layer shipping inside Intel 18A. And it did so without EUV lithography. That sounds like SMIC somehow jumped beyond Intel. It did not. Intel's overall process remains denser, more efficient, and considerably more advanced. Intel 18A can also support a tighter metal pitch than the version used in Panther Lake. But the measurement is still remarkable because it reveals how aggressively SMIC has stretched older lithography equipment. The company did not overcome the problem with one secret machine. It attacked the chip from several directions at once. Quadruple patterning, narrower cells, fewer transistor fins, contacts placed in tighter positions, and a metal network compressed almost to the practical edge of DUV manufacturing. The result is not a clean victory, it is an engineering trade. SMIC gained density, but it paid for that density with additional masks, extra processing, tighter alignment tolerances, and greater manufacturing complexity. And that trade may tell us more about the future of Chinese chip making than a simple benchmark ever could. Modern semiconductor names are misleading. 7 nanometers, 5 nanometers, 3 nanometers, 18 angstroms. These labels sound like direct physical measurements, as though every important feature inside a 7-nanometer chip must be 7 nanometers wide. That has not been true for years. Process names have become generational labels. They describe a package of manufacturing improvements rather than one universal dimension. Intel 18A does not mean every structure measures 18 angstroms. SMIC N+3 does not mean every feature measures 7 nanometers. Two companies can use completely different names while producing structures that overlap in certain dimensions. That is why comparing 7 nanometer with 18A by name alone creates the wrong picture. A chip contains many different measurements. There is gate pitch, fin pitch, cell height, transistor density, metal pitch, SRAM density, and the spacing between contacts and wires. Each reveals one part of the process. The new teardown focused attention on M0, the first local metal layer sitting just above the transistor structures. Think of the transistors as tiny buildings. The metal layers are the roads connecting them. M0 handles extremely short local connections inside the smallest logic cells. Higher layers gradually become wider roads carrying signals across larger regions of the chip. A tighter M0 pitch allows more local wiring to fit into a smaller area. But one narrow street does not automatically mean the whole city is better. The city also needs highways, power delivery, intersections, and enough space for traffic to move. That is where the comparison becomes complicated. The chip examined was Huawei's Kirin 9030 Pro, part of the processor family used in the Mate 80 series. It is manufactured using SMIC's third-generation 7nm class process, known as N+3. Researchers measured the M0 pitch at approximately 32.5 nanometers. That is around 10% tighter than the 36nm M0 configuration found in Intel's Panther Lake processors. SMIC's M1 layer measured approximately 38 nanometers, while M2 measured around 40. These dimensions show that SMIC compressed the lowest wiring layers aggressively, but the larger picture is different. The teardown estimated SMIC N+3 at roughly 113 million transistors per square millimeter using a normalized logic density metric. That places it around the level of TSMC's older N6 process. Intel 18A's high-density library remains approximately 38% denser. So how can one local layer be tighter while the overall process remains far behind? Because density is not controlled by one dimension. SMIC squeezed M0 partly because it needed to. Intel could leave more space there because it had already removed one of the largest sources of congestion: power. Traditional chips deliver both data signals and electrical power through metal layers above the transistors. Imagine trying to build a city where delivery vans, commuter traffic, power cables, and water pipes all compete for the same narrow streets. The result is congestion. Intel's Power via technology changes that arrangement. Instead of routing power through the front side metal stack, Intel brings power through the back of the silicon. Signals remain on one side. Power arrives from the other. This frees valuable routing space above the transistors and reduces resistance in the power network. With less front-side congestion, Intel does not always need to compress every local wire to the smallest possible pitch. Panther Lake uses a 36nm M0 pitch, but Intel 18A reportedly supports a 32nm option. Intel chose the looser configuration partly because Panther Lake relies heavily on higher performance cell libraries and because Power via gives designers more routing freedom. That is why the headline needs the phrase "in one critical layer." SMIC produced a tighter M0 pitch in this shipping Huawei chip. But Intel's process is not limited to 36 nanometers, and a wider M0 layer does not automatically represent weaker technology. Sometimes additional space is not a failure to shrink. It is a choice enabled by a better architecture. The most impressive part of SMIC N+3 is not that the company found a magical replacement for EUV. It is that engineers extracted more resolution from DUV lithography through repetition. The key method is called self-aligned quadruple patterning, or SAQP. The concept sounds almost like a geometric trick. A DUV lithography system first prints a relatively wide guide pattern called a mandrel. A thin spacer material is deposited along the sides of that guide. The original guide is removed, leaving the spacers behind. Those spacers then become guides for another deposition and removal cycle. One original line effectively becomes 4 narrower lines. Imagine drawing one thick stripe on a road. You place barriers along both edges, then remove the original stripe. Next, place smaller barriers around the barriers that remain. After several carefully controlled steps, one broad pattern has been multiplied into several narrow, evenly spaced features. The lithography machine did not directly resolve every final line. The process created them through deposition and etching. That is how SMIC could form a roughly 32nm grid using DUV equipment. But every added operation creates risk. The spacers must have nearly identical thickness. The etch must remove exactly the intended material. The new lines must remain aligned with contacts and structures created in other steps. If one stage shifts slightly, the error can propagate through the entire pattern. EUV can print finer features with fewer pattern-splitting steps. DUV can reach similar dimensions in selected layers, but the path is longer. SMIC replaced machine simplicity with process complexity. Quadruple patterning sounds clever because it is clever. It is also expensive. Each additional deposition, etch, cleaning, and inspection step consumes factory time. More steps require more equipment. More equipment means more maintenance. More masks increase cost before the first commercial wafer is even produced. Alignment becomes increasingly difficult because patterns created in separate operations must meet with extraordinary precision. A small overlay error can place one metal line too close to another, creating electrical leakage or a short circuit. Place it too far away, and the intended connection may fail. Then there is variation. If one spacer is slightly thicker than another, the final lines will not be identical. Resistance changes, timing changes. One region of the chip may behave differently from another. The teardown reportedly found that the tight M0 trenches had a more difficult profile than the looser metal layers above them. That does not mean the chip is defective. It means the manufacturing cost is visible in the structure. SMIC successfully created the feature, but the feature carries evidence of how hard it was to create. This is the central paradox of DUV scaling. The machine itself is older. The process surrounding it becomes more complicated. The metal layer was only part of the story. SMIC also used several design and manufacturing techniques to reduce the area of the basic logic cells. The first was fin depopulation. The Kirin 9030 uses FinFET transistors. In a FinFET, current flows through vertical silicon fins surrounded by the gate. More fins can provide stronger electrical drive, but more fins also consume space. SMIC N+3 uses 2 NMOS fins and 2 PMOS fins in its measured logic cells. Reducing the fin count allows cells to become narrower, but it can also limit drive strength. It is similar to replacing a wide multi-lane tunnel with a narrower one. The tunnel occupies less land. It may not move the same amount of traffic. The second technique is contact over active gate. Normally, the electrical contact connected to a gate may sit beside the active region, consuming additional space. Place that contact directly over the active gate, and the cell becomes shorter. Simple in a diagram. Difficult in production. The contact must land accurately without damaging or interfering with the transistor below it. The third technique is the single diffusion break. Logic cells need isolation between neighboring transistor regions. Older layouts often used a wider double break. A single diffusion break saves space, but it increases sensitivity to local manufacturing variations. Again, density improves. Margin becomes smaller. None of these ideas is unique to SMIC. Major foundries use similar density-enhancing techniques. What stands out is how aggressively SMIC combined them in one process generation. This is where the story moves beyond lithography. A foundry cannot simply shrink every shape and ask chip designers to continue as before. At these dimensions, the manufacturing process and the circuit layout must be developed together. This is called design technology co-optimization. The factory tells designers which shapes can be produced reliably. Designers reorganize logic cells around those restrictions. The factory then adjusts the process to support the new layouts. The result is a feedback loop. Suppose a transistor loses one fin to save area. The circuit may now switch more slowly. Designers compensate by changing the cell, adjusting the signal path, or using a stronger cell elsewhere. Suppose a metal layer becomes tighter but gains resistance. Engineers may shorten important routes or move selected connections to a higher layer. The process is no longer simply about drawing smaller transistors. It becomes a puzzle involving density, power, performance, heat, and manufacturability. SMIC N+3 appears to be a product of that puzzle. Its density did not come from one enormous leap in lithography. It came from dozens of smaller compromises that reinforce one another. Huawei used the denser N+3 process to fit more capability into a chip with a die area similar to its predecessor. The Kirin 9030 reportedly adds another middle CPU core, expands several caches, and increases GPU and neural processing resources. Individual CPU cores also became smaller. The prime core shrank despite receiving a larger private cache. The middle cores became significantly more compact. GPU compute units became smaller, allowing Huawei to increase the number of units while keeping the full graphics section within a manageable area. That is what process scaling is supposed to accomplish. The goal is not merely creating a beautiful cross-section under a microscope. The goal is using less area for existing functions, then spending the saved area on more capability. Huawei appears to have done that successfully, but performance reveals the limitation. The Kirin 9030 improved significantly over the previous generation, especially in graphics. It still trails current flagship processors from the leading mobile chip companies. Its CPU architecture and manufacturing efficiency remain behind the newest designs. The chip can contain more hardware than its predecessor. It cannot operate that hardware with the same power efficiency as a processor manufactured on a leading 3nm class process. Density matters. The voltage and frequency curve matters more. A smaller structure does not automatically switch faster. Narrower metal wires have greater electrical resistance. Smaller transistors can suffer from leakage and variability. More patterning can introduce dimensional differences across the wafer. A process must balance density with the ability to operate at useful voltage and frequency. This is where SMIC's disadvantage becomes clear. The Kirin 9030 is a credible modern smartphone processor, but it is not equal to the latest Apple, Qualcomm, or MediaTek flagship chips. Its strongest CPU core reportedly performs more like an older high-end design. Its GPU made a major generational jump, yet remains far behind current top-tier alternatives. Efficiency is the greater challenge. A processor can reach competitive performance by consuming more power, but a smartphone has strict thermal limits. The device cannot use a large cooling system. The battery must last. The surface cannot become uncomfortably hot. That means performance per watt determines how much of the chip's theoretical capability can be used continuously. SMIC compressed the layout. It has not yet matched the manufacturing characteristics of the most advanced nodes. In M0 pitch inside these two shipping products, yes, the Kirin 9030's measured 32.5nm pitch is tighter than Panther Lake's 36nm implementation. Across the entire manufacturing process, no. Intel 18 amps uses gate-all-around ribbon FET transistors, rather than conventional FinFETs. It includes backside power delivery. It offers substantially greater normalized logic density, and it provides a more advanced platform for performance and efficiency. Even the narrow M0 victory needs context because Intel 18A supports a tighter 32nm version that was not used in Panther Lake. So the correct interpretation is not that SMIC's 7nm process is better than Intel 18A. It is that process node names hide enormous complexity. A company working with older lithography can produce one dimension that looks more advanced than a dimension inside a newer process. But it may need more steps, more masks, and more compromise to get there. The number is real. The meaning is conditional. The significance lies in what SMIC proved can still be extracted from DUV. Many observers assumed that without EUV, advanced logic manufacturing would quickly reach a hard wall. The Kirin 9030 suggests the wall is not perfectly vertical. It is more like a steep mountain. Progress remains possible, but every meter becomes harder than the last. SMIC has tightened local metals, reduced cell dimensions, and incorporated multiple density boosters. It has reached roughly TSM6 class logic density, while using a more complicated manufacturing route. That is not parity with the leading edge. It is evidence of continued movement, and commercial shipment matters. This is not a research wafer designed only to demonstrate one small test structure. The process is manufacturing a complete smartphone system on chip containing CPU cores, graphics, AI processing, memory controllers, image processing, and communication hardware. Every one of those blocks must work together. A laboratory can optimize one line. A consumer processor must survive millions of interacting lines. That makes the result harder to dismiss. SMIC may still have additional scaling options. Cell height could be reduced again. Some local metal layers could be pushed into even more aggressive patterning. Gate pitch may shrink slightly. Future designs could use backside contacts or advanced three-dimensional stacking. But each option becomes more difficult. If another routing layer requires quadruple patterning, mask count rises again. If cells become shorter, designers lose wiring tracks. If contacts move to the backside, manufacturing requires wafer thinning, backside alignment, and new integration steps. None of these is impossible. Together, they become unforgiving. The danger is not that one individual step cannot work. The danger is that the combined process becomes too expensive, too slow, or too sensitive to variation. A foundry does not win by producing the world's most impressive cross-section. It wins by producing large numbers of functional chips at a competitive cost. That is why EUV remains so valuable. It does not perform magic. It reduces the number of tricks required. If shrinking the chip in 2 dimensions becomes increasingly expensive, the next option is to build upward. Huawei has discussed an approach called logic folding, which would divide parts of a logic block across multiple active silicon layers. Instead of placing every transistor beside the others on one flat surface, some functions could sit above or below their neighbors. Short vertical connections could replace longer horizontal wires. This could improve density per package area and reduce the time required for signals to travel across large blocks. The approach has its own difficulties. Stacked active logic creates heat. Bonding must be extremely precise. Testing becomes more complicated. The density comparison also changes because adding another layer increases transistors per package footprint without improving the transistor process itself. Still, the direction is logical. When the map cannot become much smaller, fold the map. SMIC n+3 may therefore represent both progress and a warning. It demonstrates how far planar DUV scaling can be pushed. It also demonstrates why the industry is looking beyond planar scaling. My view is that the 32.5 nanometer result is more interesting than the phrase "China beat Intel" suggests. A simple victory would almost be less revealing. SMIC did not create a universally superior process. It created an unusually aggressive one. The company used quadruple patterning, tighter local wiring, and several layout optimizations to achieve a dimension that looks extraordinary beside Intel's shipping configuration. But Intel's wider M0 layer exists partly because PowerVia removed power congestion from the front side. Intel could afford not to squeeze that layer as hard. One company compressed the road because space was scarce. The other redesigned the city so the road did not need to carry everything. Both are engineering achievements. The difference is cost and headroom. SMIC's approach demonstrates ingenuity, but each additional shrink will demand more complexity. Intel's architecture gives it more room for future optimization. So no, the Kirin 9030 does not prove that China has overtaken Intel. It proves something narrower, and still significant. Sometimes it comes from taking an old tool, surrounding it with new processes, and forcing it to perform one more task that looked unreasonable. The final product may cost more. It may consume more power. It may remain behind the leader overall, but it works. And once something works in a commercial chip, the question changes. It is no longer, can this be done? It becomes, how far can they push it next? So what do you think? Is SMIC's 32.5 nanometer metal pitch evidence that DUV lithography still has meaningful life left? Or does the added cost and complexity prove that this approach is approaching its practical limit? Let me know your position in the comments. And if you want more grounded breakdowns of the machines, materials, and hidden engineering choices shaping the semiconductor industry, subscribe to Eastern Engine. Because sometimes the most important part of a processor is not the feature advertised on the box. It is the wire buried at the very bottom of the chip. Alibaba has spent years building one of the largest cloud businesses in China. But now, it is making a much bigger move. The company has unveiled a new artificial intelligence chip called the Zhenwu M890, a new networking processor, a new software stack, and a rack-scale system that places 128 AI accelerators inside a single unit. Alibaba calls that system the Pangeo AL128. And the important part is not simply that China has produced another AI chip. The important part is that Alibaba is trying to build the entire computing platform around it. The chip, the interconnect, the software, the cloud service, and the AI models are all being developed inside the same corporate ecosystem. That is the strategy that made NVIDIA so difficult to challenge. And it is now the strategy Alibaba is attempting to reproduce inside China. So has China just created a serious new NVIDIA rival? Or is Alibaba still years away from matching the hardware, software, and manufacturing scale NVIDIA already controls? To answer that, we need to look beyond the headline and examine what Alibaba has actually built. The chip at the center. The Zhenwu M890 was developed by T-Head, Alibaba's semiconductor design subsidiary. Alibaba says the processor delivers 3 times the performance of its previous Zhenwu 810E. That comparison is important. Alibaba did not claim that the M890 is 3 times faster than an NVIDIA H100, H200, or Blackwell processor. The 3 times figure refers only to Alibaba's own previous generation chip. The company has not published enough independently verified benchmark data to prove that the M890 can beat NVIDIA's leading products. But the specifications reveal what Alibaba is trying to optimize. The M890 includes 144 gigabytes of memory and supports precision formats ranging from FP32 down to FP4. Higher precision formats are useful when accuracy matters, while lower precision formats can make AI inference faster and cheaper. The processor also includes 800 gigabytes per second of inter-chip bandwidth. Those features target AI agents, systems that do more than answer one question. An agent may search databases, call software tools, coordinate with other agents, remember long sequences, and complete tasks that continue for hours. That creates heavy demands on memory and communication. A processor may be powerful on paper, but if it cannot move data quickly enough between chips, much of that computing power remains underused. This is why Alibaba is presenting the M890 as the foundation of a larger machine. The 128-chip server. The Panju Ali 128 integrates 128 AI accelerators into one rack-scale system. Alibaba says the server can deliver internal bandwidth at the petabyte per second scale. That does not mean one chip performs at that level. It means the rack is designed to move enormous amounts of data between accelerators. This system-level approach has become essential because modern AI models have grown too large for one processor. Training and inference now depend on hundreds or thousands of chips working together. If the connection between chips is slow, processors sit idle while waiting for data. If communication is fast and predictable, the cluster becomes more efficient. Alibaba has therefore created a dedicated networking chip called ICN Switch 1.0. The company says it provides up to 25.6 terabits per second of aggregate bandwidth and supports full bandwidth connections across 64 accelerators. Alibaba also introduced a proprietary software platform called T-Head Sail, designed to extract performance from the hardware. Together, the M890, the networking chip, Sail, and the Panju server form an attempt to control the complete AI computing stack. Why the full stack matters. NVIDIA's dominance was never built only on transistor counts. Its strongest advantage is CUDA, the software ecosystem developers use to program NVIDIA graphics processors. Over many years, CUDA accumulated libraries, tools, training materials, optimized code, and a massive developer community. A company purchasing NVIDIA hardware is not simply purchasing chips. It is purchasing access to an ecosystem that already supports thousands of workloads. That creates high switching costs. Even if another company produces a competitive accelerator, customers may hesitate because their engineers, models, and software pipelines were built around CUDA. Alibaba understands this problem. That is why it is connecting its hardware directly to Alibaba Cloud, its Balium model platform, and its Qwen family of AI models. The company can design chips around workloads running inside its own cloud and optimize the software and models together. The goal is not necessarily to produce one standalone processor that defeats NVIDIA in every benchmark. The goal is to reduce dependence on NVIDIA by building a tightly integrated alternative for Alibaba's own cloud ecosystem. Why Alibaba needs its own chips? Alibaba has historically been a major buyer of NVIDIA processors. Like other Chinese technology companies, it preferred NVIDIA because the hardware was powerful, the software mature, and developers already knew how to use it. But that dependence became a strategic weakness as the United States expanded export restrictions on advanced AI hardware. A chip permitted 1 year could require a license the next. Products designed specifically for China could later become restricted. For a cloud provider building data centers that must operate for years, uncertainty itself becomes a cost. Alibaba cannot base its entire AI strategy on the assumption that every future NVIDIA generation will remain available. Domestic chips provide another option. Even if they are less powerful or efficient, they can offer a supply chain that is more predictable inside China. This does not mean Alibaba no longer wants NVIDIA products. Chinese technology companies have continued showing interest in NVIDIA hardware whenever access becomes possible. But Alibaba now has a strong incentive to ensure NVIDIA is no longer its only path to advanced computing. From experiment to real deployment. One reason the M890 deserves attention is that T-Head is no longer a small laboratory project. Alibaba says more than 560,000 Zhenwu processors have been shipped across all generations. More than 400 external customers in 20 industries have deployed them, including companies in automotive and financial services. Those figures are cumulative and should not be confused with shipments of the new M890 alone. Alibaba has not disclosed how many M890 processors it can manufacture or how quickly it can produce them. Still, the installed base shows T-Head has moved beyond prototypes. IDC data, reported for 2025, estimated that T-Head shipped around 265,000 AI accelerators in China, placing it behind Huawei, but ahead of several other domestic suppliers. That does not make Alibaba a global NVIDIA competitor, but it does make it one of China's most important domestic AI chip suppliers, with a cloud platform capable of consuming its own hardware at enormous scale. The Huawei question. Alibaba's most immediate competitor may not be NVIDIA. It may be Huawei. Huawei has become the leading Chinese supplier of domestic AI accelerators and has built its own Ascend hardware, networking systems, software tools, and large-scale clusters. but Alibaba has reasons to avoid complete dependence on Huawei. The two companies compete in cloud services, enterprise software, AI, and consumer technology. Alibaba's own chips allow it to control cost, product schedules, software integration, and cloud capacity. This could produce a new structure inside China. Huawei may lead the broader domestic accelerator market. Alibaba may optimize T-head chips for Alibaba Cloud and Qwen. Baidu may continue developing Kunlun Xin. Instead of one Chinese replacement for NVIDIA, China may develop several competing ecosystems. That fragmentation creates software problems, but it may also accelerate innovation. The manufacturing problem. Designing a chip is only one part of the challenge. Manufacturing it at high volume is much harder. Alibaba has not publicly disclosed all important details about the M890's fabrication process, production yield, advanced packaging, or memory supply. These omissions matter. NVIDIA benefits from access to TSMC's leading manufacturing technology, advanced packaging capacity, and a global supply chain for high-bandwidth memory. Chinese chip designers operate under restrictions that limit access to some of the world's most advanced semiconductor equipment and services. A design may look impressive, but customers need thousands of reliable processors delivered on schedule. If Alibaba cannot produce enough M890 chips, the Panju architecture will remain limited. Low yields or high power consumption could make deployment expensive. This is the largest unanswered question. Alibaba has revealed the architecture. It has not revealed whether it can manufacture the platform at the scale required to challenge NVIDIA or Huawei. Performance without independent benchmarks. Another uncertainty is real-world performance. The headline numbers come from Alibaba. There are not yet enough independent tests comparing the M890 with NVIDIA, Huawei, AMD, or other accelerators across the same models and power limits. AI chip comparisons are complicated. A system may be fast for Alibaba's Qwen models but less efficient for workloads designed around CUDA. This is why the M890 should not be described as an NVIDIA killer. There is no evidence it has defeated NVIDIA's latest products across the board. The more accurate conclusion is that Alibaba has built a credible domestic platform that may be good enough for a growing range of Chinese workloads. In a restricted market, good enough can be extremely valuable. An available chip with stable local support may be more useful than a faster foreign chip customers cannot reliably purchase. The roadmap signal. Alibaba has also outlined a multi-year plan. The company says the M890 will be followed by the V900 in the third quarter of 2027 and the J900 in the third quarter of 2028. Roadmaps are promises, not completed products. But publishing a roadmap tells customers that T-head is not intended as a temporary response to export controls. Alibaba wants enterprises to commit software, engineers, and infrastructure to a platform that will continue improving. The company has also committed more than 380 billion yuan, approximately $53 billion, to cloud and AI infrastructure over 3 years. The investment covers far more than chip design, but domestic silicon is clearly becoming part of Alibaba's long-term cloud strategy. What this means for NVIDIA. NVIDIA is still far ahead globally. It leads in accelerator performance, software, developer adoption, networking, and complete data center systems. Alibaba has not shown it can replace NVIDIA for every frontier training workload. But NVIDIA does not need to lose globally for this development to matter. China is one of the world's largest technology markets. Every workload moved to T-head hardware reduces the number of future Chinese systems built entirely around CUDA. Every engineer trained on SAIL becomes less dependent on NVIDIA. Every Qwen model optimized for Alibaba hardware makes the domestic platform more useful. This creates a feedback loop. More chips produce more users generate more software attracts more customers. That is the mechanism that helped NVIDIA build its dominance. The difference is that Alibaba's ecosystem is being accelerated by export controls, domestic policy, and the company's enormous cloud customer base. My take is that the Zhenwu M890 is important, but not because it has already beaten NVIDIA. It is important because Alibaba has crossed the line from designing individual chips to constructing a complete AI infrastructure platform. The Panju AL128 combines 128 accelerators, dedicated networking, proprietary software, cloud access, and models developed inside one ecosystem. That vertical integration gives Alibaba a path to improve the whole system, even when it cannot match NVIDIA chip for chip. There are still serious unknowns. We do not know the true manufacturing scale of the M890. We do not have enough independent performance data. We do not know whether developers outside Alibaba's ecosystem will embrace sale. And we do not know whether the 2027 and 2028 roadmap will remain on schedule. But the direction is clear. China's AI hardware market is no longer waiting for one national champion to replace NVIDIA. Huawei is expanding. Alibaba is building its own stack. Baidu and other suppliers are developing alternatives. Chinese models are being optimized for domestic infrastructure. The result may not be one chip that defeats NVIDIA. It may be an entire market that gradually learns how to operate without NVIDIA. That is the real threat. NVIDIA cannot easily reverse the political and commercial incentives pushing Chinese companies towards self-reliance. Alibaba's 128-chip server is therefore more than a piece of hardware. It is a signal that China's largest cloud companies are preparing for a future in which access to American chips can never be guaranteed. So what do you think? Can Alibaba turn the Zhenwu M890 and Panju AL128 into a genuine alternative to NVIDIA? Or will manufacturing limits and software compatibility keep China's domestic accelerators behind? Let me know your view in the comments. And subscribe to Eastern Engine for more grounded coverage of the chips, factories, and engineering decisions reshaping the global economy. Because NVIDIA still leads the global AI industry, but Alibaba is building a system designed to make that lead less important inside China. China may have just moved one of the most important parts of artificial intelligence hardware away from organic circuit boards and toward glass. BOE, the Chinese company best known for display panels, says it has completed a large, high-layer count glass core substrate sample for advanced chip packaging. The structure uses a 929 build with 20 total layers. More importantly, BOE says the sample passed demanding reliability tests, including 1,000 thermal compression bonding cycles, moisture tests, high-temperature storage, low-temperature storage, and preconditioning. That does not mean China has mass-produced a finished glass AI processor. It does not mean silicon has disappeared. And it does not mean every copper connection inside a computer is about to vanish. But it does mean glass packaging is moving from concept demonstrations toward hardware that can survive the stresses expected in manufacturing and operation. BOE is also forming a dedicated team to develop micro-LED optical interconnects and glass substrate co-packaged optics. The future bottleneck inside AI systems may not be computing power. It may be the copper wiring carrying data between processors, memory, and network devices. If glass substrates can support larger packages, finer wiring, better dimensional stability, and optical links placed closer to chips, they could change how future AI computers are assembled. So has China built a 20-layer glass AI chip that could end copper? But it may have passed one of the tests required to make that possibility serious. What Bo actually built? A modern AI accelerator is not simply one small silicon rectangle. The finished product can include multiple computing dies, high-bandwidth memory stacks, power delivery components, controllers, and communication links. These parts must be positioned, powered, cooled, and connected with extraordinary precision. The structure supporting them is called a package substrate. It sits between the silicon devices and the larger system board, carrying power and signals across thousands of tiny electrical connections. Most advanced substrates today use organic materials. But as packages grow larger and wiring becomes denser, organic substrates face physical limitations. They can expand, shrink, bend, or warp during heating and cooling. Even tiny dimensional changes matter when engineers align extremely fine connections across a package containing many chiplets. Glass offers a different foundation. It can remain flatter across large areas, provide strong dimensional stability, support very fine features, and offer useful electrical properties for high-speed signals. BOE says its 20-layer sample uses a 929 configuration. In simple terms, that means 9 buildup layers on one side, a central 2-layer glass core section, and another 9 buildup layers on the opposite side. The design matters because advanced packages need many routing layers to distribute power and connect processors, memory, and external interfaces. Building a large 20-layer substrate that remains aligned and reliable is much harder. Why the reliability test matters. Computing hardware repeatedly heats during operation and cools when workloads stop. Different materials expand at different rates. That creates stress around copper vias, solder joints, wiring layers, and interfaces. High temperatures can weaken materials, while low temperatures can create contraction and cracking. Manufacturing steps such as bonding add pressure and heat before the package reaches a customer. BOE says its samples passed several industry reliability tests. One was thermal compression bonding cycling, reported at 1,000 cycles. Thermal compression bonding uses controlled heat and pressure to create fine electrical connections. Repeated cycling helps reveal whether interfaces separate, crack, or lose electrical performance under stress. The sample also reportedly passed accelerated temperature and humidity testing, biased humidity testing, high-temperature storage, low-temperature storage, and preconditioning. These tests do not prove the substrate will survive every product, factory process, or operating environment. The company is testing whether a complex multi-layer structure can remain functional after repeated environmental and manufacturing stress. That is essential before chip companies will trust a new substrate beneath expensive processors and memory. Why AI packages keep getting bigger? One package may contain several compute dies and multiple stacks of high-bandwidth memory. A single piece of silicon cannot grow forever. Manufacturing defects become more expensive as die size increases, while practical size is limited by lithography equipment. Chip makers therefore divide large designs into smaller chiplets and connect them inside one package. But it moves a major engineering challenge from the silicon die into the package. The substrate must connect many devices with enough bandwidth that they behave like one system. It must remain flat enough for thousands of fine connections to align correctly. And it must support larger physical dimensions without warping. Glass is attractive because it can pick ratio through glass via formation, deep hole copper filling, low-stress metallization, multi-layer lamination, high-density routing, and low-stress cutting. Those processes turn plain glass into a usable electronic platform. The copper bottleneck. The title says copper may be finished. Copper is not disappearing from electronics. Even BOE's glass substrate relies on copper-filled vias and metal wiring. Power delivery will still require conductive paths, and short electrical connections will remain essential. The real problem is distance and bandwidth. As data rates increase, copper links consume more energy and become harder to operate reliably across longer paths. Electrical signals lose strength, generate heat, interfere with nearby channels, and require increasingly complex equalization. Inside a large AI system, processors and memory must move enormous quantities of data every second. Engineers can improve copper, but the energy cost per transmitted bit is becoming a concern. Optical communication sends information using light. Light can move large amounts of data with lower loss across distance and reduced electromagnetic interference. The industry already uses optical transceivers for many network links. The next step is bringing optical components much closer to the processor. That idea is called co-packaged optics. Instead of sending high-speed electrical signals from a chip across a long board to a separate optical module, optical engines are placed near or inside the main package. The electrical path becomes shorter. This can reduce power consumption and support higher bandwidth. Why glass and optics fit together? Glass is interesting for optical integration. It is dimensionally stable, can support precise structures, and can provide a platform for electrical routing and optical components. BOE says it formed a project team focused on micro-LED optical interconnect systems and glass substrate co-packaged optics. Micro-LEDs are extremely small light-emitting devices. They are best known as display technology, but their size and fast response make them candidates for short-distance optical communication. A micro-LED array could potentially transmit many optical channels in parallel across short distances. That could help AI servers move enormous bandwidth between nearby devices while minimizing power. BOE has decades of experience processing large glass panels and developing display technologies, including micro-LED manufacturing. The company is trying to reuse those capabilities in semiconductor packaging and optical interconnects. Display manufacturing and advanced chip packaging have different tolerances, materials, customers, and reliability demands. But BOE already understands large area glass processing, precision patterning, multi-layer structures, and mass production automation. From display factory to chip packaging, BOE's move is part of a larger shift. Display manufacturers built factories capable of processing large glass panels with fine patterns, thin films, and precise alignment. Advanced semiconductor packaging is one of those markets. BOE brought a glass core substrate pilot line online with a design capacity of roughly 1,000 substrates per month. The company says it delivered samples to domestic customers. Some customers reportedly completed concept verification and entered technical testing. However, BOE also says the business has not reached mass production and has not generated mass production revenue. That distinction matters. A pilot line proves samples can be produced repeatedly. It does not prove competitive yield, cost, throughput, or customer adoption. For a commercial AI package, Every substrate must meet strict specifications. A small defect can ruin a product containing extremely expensive processors and memory. The challenge is not producing one successful piece. It is producing thousands with consistent quality at a price customers will accept. The global glass race. China is not alone in pursuing glass substrates. Intel has spent years researching glass core packaging. Other substrate makers, equipment companies, foundries, and display manufacturers are also developing glass processes. The attraction is global because every major AI chip company wants more memory bandwidth, more chiplets, larger packages, lower power, and faster interconnects. Glass is one possible solution, not the only one. Organic substrates continue improving. Silicon interposers remain important for extremely dense connections. Fan-out packaging, advanced bridges, and new redistribution technologies are also evolving. The winning architecture may combine several materials rather than replacing everything with glass. China's significance comes from manufacturing scale. If BOE adapts large panel glass processing to semiconductor requirements, it could build substrates using panel-level methods rather than treating every package like a small wafer. Panel processing may increase the number of large substrates produced per cycle, but larger panels also create more opportunities for defects, alignment errors, stress, and breakage. The economic advantage exists only if yields become high enough. What the 20-layer result does not prove, the reliability milestone is important, but several things remain unproven. BOE has not announced a commercial AI accelerator shipping on this substrate. It has not disclosed the customer, final package design, production yield, selling price, or long-term field reliability. The company has not shown that its glass substrate is superior to every competing organic, silicon, or glass solution. Its optical interconnect project is still under development. A dedicated team is not the same as a finished co-packaged optics product. The phrase "copper may be finished" should be understood as a direction, not a completed transition. Copper links are reaching limits in the highest bandwidth parts of AI systems. Optics may gradually replace longer, faster electrical connections. But copper will remain inside packages, boards, power systems, and many short-reach links. The likely future is hybrid. Electricity will deliver power. Copper will handle many local connections. Optical links will move increasing amounts of data where electrical transmission becomes inefficient. Glass could become the platform allowing those technologies to coexist inside one large package. Why this matters for China? Advanced packaging is strategically important because computing performance no longer depends only on manufacturing the smallest transistor. A company can combine chips, memory stacks, and optical links to create a powerful system even when individual dies use different process nodes. Packaging does not erase the value of leading-edge fabrication. It gives engineers another path to improve performance. China faces restrictions on advanced semiconductor equipment and high-end AI hardware. That creates pressure to improve every part of the domestic computing stack. Glass substrates, panel-level packaging, optical interconnects, domestic memory, and chiplet integration can help China extract more performance from available chips. BOE represents a different type of semiconductor competitor. It is entering through glass, displays, micro-LEDs, and large-scale panel manufacturing rather than a traditional foundry. That cross-industry approach could create new options if conventional substrate suppliers cannot scale quickly enough for AI demand. My take is that BOE's 20-layer reliability result is meaningful, but the headline should not be mistaken for a finished revolution. China has not replaced silicon with glass. BOE has not eliminated copper, and a pilot line producing customer samples is not a mature commercial supply chain. What BOE has done is more specific. It built a large, complex glass core substrate, developed processes to route signals and power through it, and pushed the sample through serious reliability testing. At the same time, it is connecting that glass strategy to micro-LED optical interconnects and co-packaged optics. That combination matters, because future AI systems need larger packages and faster, more efficient communication. Glass may help solve the mechanical problem. Optics may help solve the bandwidth problem. If BOE combines them economically, China could become an important supplier of the platform beneath future AI chips, even without manufacturing the processors themselves. The next test is not another laboratory record. It is customer qualification, production yield, cost, and deployment inside a real computing product. So what do you think? Will glass substrates and optical links become the foundation of future AI hardware? Or will manufacturing complexity keep organic packages and copper connections dominant? Let me know your view in the comments. And subscribe to Eastern Engine for more grounded coverage of the chips, factories, and engineering decisions reshaping the global economy. Because the race for AI leadership is no longer happening only inside the transistor, it is also happening beneath the chip, between the memory, and across every connection carrying the data. BYD became one of the world's most powerful electric vehicle manufacturers by mastering batteries, electric motors, electronics, and mass production. Now the Chinese company wants to use those same capabilities to build something very different: humanoid robots. BYD Executive Vice President Stella Li says her goal is to place 2 or 3 humanoid robots inside every BYD showroom. The robots could greet customers, explain vehicle features, demonstrate technology, and make the buying experience more interactive. Li believes the necessary technology could become commercially available within the next 1 or 2 years. But the showroom is only the beginning. BYD is also developing robots for factories, service industries, and eventually homes. The company is even considering highly automated factories that could operate with minimal human presence. That puts BYD on a collision course with Tesla. For years, Tesla has argued that it should not be viewed simply as a car company. Elon Musk has repeatedly presented Tesla as an artificial intelligence and robotics company that happens to manufacture vehicles. Optimus, Tesla's humanoid robot, is central to that vision. But BYD's entry changes the competition. The next major fight between Tesla and China may not be about electric cars at all. It may be about which company can turn the automobile supply chain into a robot industry. Why BYD wants robots in showrooms? A humanoid robot inside a car dealership sounds like a publicity stunt. But from BYD's perspective, a showroom is an unusually practical place to begin. The environment is controlled. Floors are flat. Products are arranged predictably. The robot does not need to navigate a crowded construction site or an unfamiliar home. It can perform a limited number of repeatable tasks. It can welcome customers, answer common questions, point towards specific vehicles, explain charging features, and guide buyers through available configurations. The robot could also operate as a moving demonstration of BYD's engineering capabilities. Customers would not only see an electric car, they would see batteries, motors, sensors, software, artificial intelligence, and robotics working together in one physical machine. Stella Li has emphasized that robots would not eliminate the need for human salespeople. Buying a vehicle involves emotion, negotiation, trust, and personal preferences. A robot may explain a feature clearly, but it cannot necessarily replace the connection between a customer and an experienced employee. The more realistic strategy is to use robots as assistants. They could handle repetitive explanations while human employees focus on questions requiring judgment and personal attention. Showrooms would also provide BYD with valuable real-world testing. Engineers could study how customers react, which questions are difficult, where the robot becomes confused, and how reliably it operates throughout the day. That information would help improve future versions before robots move into less predictable environments. Why car companies are building humanoids. At first glance, a humanoid robot appears unrelated to an electric car, but the two products share more technology than many people realize. An electric vehicle needs batteries, electric motors, power electronics, cameras, sensors, processors, software, cooling systems, and advanced manufacturing. A humanoid robot needs almost the same categories of components. Its battery stores energy. Electric actuators move its arms, legs, hands, and joints. Cameras allow it to perceive its surroundings. Processors interpret visual information and coordinate movement. Software decides how the machine should respond. The physical design is different, but much of the industrial knowledge overlaps. This gives electric vehicle companies an advantage over ordinary software startups. A robotics startup may have excellent artificial intelligence but little experience producing complex machines at scale. A traditional automaker already understands factories, suppliers, quality control, logistics, safety testing, and cost reduction. BYD has an additional advantage because it produces many important components internally. The company began as a battery manufacturer before becoming a major vehicle producer. It developed expertise in battery chemistry, power semiconductors, electric drive systems, electronics, and automated manufacturing. Those capabilities can be redirected toward robotics. A robot must become cheaper, more reliable, and easier to manufacture before it can move from a laboratory demonstration into ordinary businesses. That transition is exactly where large industrial companies may be strongest. From car factories to dark factories. BYD's humanoid ambitions are not limited to customer-facing robots. The company also wants robots inside its manufacturing operations. Factories are one of the most obvious early markets for humanoid machines. Industrial robots already weld vehicle bodies, move components, apply paint, and perform other repetitive tasks. However, most conventional industrial robots are fixed in place and designed for one specific operation. A humanoid could theoretically move between workstations and use equipment originally designed for people. It could carry parts, inspect products, operate tools, or perform tasks that change from one production run to another. This flexibility is the central promise. Instead of rebuilding an entire production line around a specialized machine, a company could train a general-purpose robot to work inside an existing human environment. BYD has discussed the possibility of dark factories within approximately 3 to 5 years. A dark factory is an extremely automated facility that requires so few people that some areas could operate without normal lighting. The term does not necessarily mean every employee disappears. Maintenance, engineering, supervision, safety, and quality control may still require people, but the production floor could become far more automated than a conventional car plant. Humanoid robots would not be the only machines inside such a factory. They would work alongside robotic arms, automated transport vehicles, machine vision systems, and intelligent production software. The goal would be continuous manufacturing with fewer interruptions, lower labor requirements, and faster adaptation. Tesla's Optimus vision. Tesla recognized the connection between vehicles and humanoid robots earlier than most global automakers. The company revealed Optimus in 2021 and presented it as a general-purpose machine capable of performing dangerous, repetitive, or boring work. Tesla's long-term argument is that physical labor represents an enormous market. If a useful robot can perform tasks across factories, warehouses, offices, and homes, demand could eventually exceed demand for cars. Tesla believes its experience with electric vehicles gives it the necessary building blocks. The company designs batteries, motors, power systems, computer hardware, cameras, and artificial intelligence software. Its factories also provide controlled environments where robots can be tested internally before being offered to outside customers. Tesla has continued preparing production capacity for Optimus, although the timing and scale of commercial manufacturing remain uncertain. Humanoid robots are far harder to mass-produce than promotional demonstrations suggest. Walking across a stage is not the same as completing useful work for 8 hours. The robot must balance, recognize objects, manipulate tools, recover from mistakes, and operate safely around people. The hands may be the most difficult component. Human hands combine strength, sensitivity, flexibility, and extremely precise control. A useful humanoid robot must handle delicate objects without dropping or crushing them. It must also perform thousands of movements without frequent mechanical failure. Tesla may have a head start in public attention and development time, but it no longer has the field to itself. China's robotics ecosystem BYD is entering one of the most competitive robotics markets in the world. China already has a dense network of companies producing electric motors, actuators, sensors, batteries, gearboxes, cameras, and industrial robots. Many of these suppliers developed alongside the electric vehicle industry. That means Chinese humanoid manufacturers can access a large domestic component ecosystem. Companies such as Unitree and UB Tech have already gained attention with walking robots, factory trials, public demonstrations, and increasingly capable humanoid platforms. Another Chinese electric vehicle manufacturer, XPeng, is preparing to mass-produce its iron humanoid robot by the end of 2026. XPeng plans to use its robots inside retail stores before expanding into broader commercial markets. Its chief executive has personally taken control of the robotics division, showing how strategically important the project has become. XPeng also connects humanoids to a larger physical artificial intelligence strategy that includes autonomous vehicles, robotaxis, and flying cars. This is becoming a pattern. Chinese electric vehicle companies are no longer treating cars as their final product. They see the car as a platform that helped them develop batteries, motors, sensors, computing systems, factories, and artificial intelligence. Robots are the next platform. Why humanoid robots are still difficult. The investment is real, but the technology remains immature. Humanoid robots look impressive in carefully prepared demonstrations. Real commercial environments expose their weaknesses. Battery life is limited. Motors generate heat. Mechanical joints wear out. Hands struggle with unfamiliar objects. Software can become confused by unexpected movement, poor lighting, noise, or crowded spaces. A human worker can immediately adapt when a box is placed in the wrong location. A robot may stop completely. Reliability is especially important in factories. A machine that works 90% of the time may look successful during a short demonstration. On a production line, 10% failure would be unacceptable. Every interruption can delay other machines and reduce the output of the entire facility. Safety is another challenge. A humanoid robot is heavy, powerful, and designed to move near people. The software must prevent collisions and react correctly when someone suddenly steps into its path. Companies must also decide whether a humanoid is actually the most efficient design. Human-shaped robots are useful in spaces built for people, but specialized robots can be cheaper, faster, and more reliable for many tasks. A warehouse may benefit more from wheeled machines than from robots walking on two legs. A factory may prefer fixed robotic arms for repetitive assembly. Humanoids must prove that their flexibility justifies their complexity. The economics will decide the winner. The robotics race will not be won by the company producing the most impressive video. It will be won by the company that can deliver useful work at a competitive cost. Businesses will compare the robot's purchase price, maintenance cost, energy consumption, reliability, productivity, and expected lifetime. A robot that costs less than a worker but requires constant repairs may not save money. A more expensive robot could still be valuable if it operates continuously and performs several different tasks. Manufacturing scale will therefore matter enormously. Tesla and BYD both understand how to reduce costs through production volume. They negotiate with suppliers, redesign components, automate assembly, and spread development expenses across large numbers of units. China's broad manufacturing network could give BYD access to lower-cost components and faster supplier competition. Tesla may benefit from stronger artificial intelligence branding, accumulated robot development, and direct integration with its software systems. The winner may not be the company with the most human-looking machine. It may be the company that reaches acceptable performance at the lowest total cost. What this means for Tesla BYD has already challenged Tesla in electric vehicles through aggressive pricing, battery integration, rapid product development, and manufacturing scale. Humanoid robots could repeat the same pattern. Tesla creates a bold vision and attracts global attention. Chinese manufacturers then compete through faster industrialization, dense supplier networks, and lower production costs. However, BYD's success is not guaranteed. Building cars does not automatically solve robotics. The company must develop sophisticated artificial intelligence, reliable hands, safe movement, and useful software. It must also prove that showroom and factory robots create real economic value. But BYD does not need to defeat Optimus immediately. It only needs to establish a working platform, test it inside its own operations, and improve it through repetition. Its showrooms provide public testing environments. Its factories provide industrial testing environments. Its dealer network could eventually become a sales and service network for robots. That combination is powerful. My take is that BYD's showroom plan matters, because it reveals how the company intends to enter robotics gradually. It is not beginning with the impossible promise of a robot that can perform every household task. It is starting with controlled environments, where the machine can provide limited but visible value. From showrooms, the robot can move into factories. From factories, it may eventually move into services and homes. Tesla is following a similar path by testing Optimus inside its own industrial operations. The difference is that China now has an entire ecosystem trying to commercialize humanoids at the same time. BYD, XPeng, Unitree, UB Tech, and many component suppliers are competing, learning, and reducing costs. That could accelerate development faster than any single company expects. The electric vehicle race proved that China can turn an emerging technology into a massive manufacturing industry. Humanoid robots may be the next test. So what do you think? Will BYD become a serious competitor to Tesla in humanoid robotics? Or are showroom robots still more marketing than useful technology? Let me know your view in the comments, and subscribe to Eastern Engine for more grounded coverage of the factories, machines, batteries, and engineering decisions reshaping the global economy. Because BYD may still be known for electric cars today, but its next major product might walk into the showroom on two legs. Silicon has been the foundation of the modern world for more than half a century. Every smartphone, every gaming PC, every AI server, every data center, every satellite, every electric vehicle, and nearly every advanced electronic system relies on one material more than any other. Silicon quietly became the invisible backbone of civilization. It powered the internet, fueled the smartphone revolution, and now drives the AI race that has reshaped the global economy. For decades, the assumption seemed impossible to challenge. If you wanted faster chips, you improved silicon. If you wanted smarter AI, you built more silicon. If you wanted more computing power, you invested billions into making silicon smaller, faster, and more efficient. But what if the entire industry has been chasing the wrong answer? Because while much of the world continues investing hundreds of billions of dollars into squeezing another few percentage points out of silicon, researchers in China have been quietly pursuing something far more ambitious. Instead of asking how to improve silicon, they asked a completely different question: what comes after it? That question has suddenly become one of the biggest discussions inside the semiconductor industry. Not because silicon is disappearing tomorrow, but because the physical limits that engineers have warned about for years are becoming increasingly difficult to ignore. As transistors shrink toward atomic dimensions, every new manufacturing generation becomes exponentially more expensive, more complicated, and more difficult to produce. The roadmap that carried computing for decades is beginning to slow down. And whenever one era starts slowing, another usually begins. Across China, universities, research institutes, advanced laboratories, photonics companies, material scientists, and semiconductor manufacturers are all exploring technologies that could fundamentally change how information moves through computers. Some projects focus on light instead of electricity. Others replace traditional semiconductor materials with entirely different compounds. Some abandon conventional transistor designs altogether. Individually, many of these breakthroughs seem incremental. Together, they begin to paint a picture of where computing may be heading next. That possibility is making investors, governments, and technology companies pay very close attention. Because replacing silicon wouldn't simply create another faster processor. It could reshape AI infrastructure, data centers, telecommunications, cloud computing, autonomous vehicles, defense technologies, and countless industries built on digital hardware. And unlike previous generations of chip improvements, this transition may not simply be about making today's computers faster. It could redefine what computers actually are. The reason this matters now is because artificial intelligence has changed the rules. Modern AI models require staggering amounts of computational power. Companies are building data centers consuming gigawatts of electricity. GPU clusters now contain tens of thousands of processors communicating simultaneously. Memory systems struggle to keep pace. Heat generation continues increasing. Power consumption rises year after year. Ironically, many of today's biggest AI limitations are no longer caused by software. They're caused by physics. Moving electrical signals through microscopic copper wiring generates resistance, heat, latency, and energy loss. Shrinking transistors further introduces quantum effects that engineers spent decades trying to avoid. Every new manufacturing node requires increasingly expensive lithography equipment and unprecedented engineering precision. Silicon hasn't stopped working. It's simply becoming much harder to improve. That reality has pushed scientists around the world to search for alternatives that were once considered experimental. Photonic computing, advanced glass materials, optical interconnects, wide bandgap semiconductors, two-dimensional materials, and entirely new computing architectures have all moved from academic research into serious engineering programs. China has invested heavily across nearly all of these fields. Some of those investments are beginning to produce results that have attracted attention well beyond China's borders. The conversation is no longer whether alternative technologies will exist. The real question has become which country commercializes them first, because history shows something remarkably consistent. The companies that dominate one generation of computing rarely dominate the next without adapting. Mainframes gave way to personal computers. Desktop computing gave way to smartphones. Traditional CPUs were joined by GPUs. AI accelerators emerged alongside them. Every technological transition created new leaders, while forcing established giants to reinvent themselves. The next transition may prove even larger. If silicon eventually stops being the default foundation for advanced computing, entire supply chains could shift. Manufacturing priorities would change. Equipment vendors would adapt. Software developers would optimize for different hardware. Data centers could be redesigned from the ground up. That doesn't mean silicon suddenly disappears. Far from it. Silicon will almost certainly remain essential for years, perhaps decades. But the industry's focus may gradually move toward hybrid systems where silicon works alongside entirely new technologies rather than carrying the entire workload alone. And that's where China's latest research becomes especially interesting. Because instead of trying to replace every silicon chip overnight, many of its projects focus on replacing only the components where silicon performs worst. Communication between chips, high-speed data transfer, AI memory bottlenecks, heat generation, optical computing. Advanced materials. One breakthrough at a time. Individually, none of these developments may seem revolutionary. Combined, they could represent the early stages of something much bigger, a transition away from an era that has defined computing for more than 50 years. And if that transition accelerates faster than expected, the biggest question won't simply be whether silicon has reached its limits. It will be who built what comes next. To understand why researchers are searching beyond silicon, you first have to understand how extraordinary its success has been. Silicon didn't become the world's dominant semiconductor by accident. It offered an almost perfect combination of affordability, stability, electrical performance, and manufacturability. As fabrication techniques improved, engineers discovered they could place more transistors onto a single chip while reducing cost per calculation. That simple trend became the engine behind modern computing for decades. Every 2 or 3 years, processors became faster, smartphones became smarter, video games became more realistic, cloud computing became practical. Artificial intelligence evolved from science fiction into everyday reality. Silicon made all of it possible, but every technology eventually reaches a point where improvement becomes increasingly difficult. For silicon, that challenge arrives at the atomic scale. Modern transistors are now measured in just a few nanometers. At these dimensions, engineers aren't simply designing electronic circuits anymore. They're designing around the strange behavior of quantum mechanics. Electrons begin leaking through barriers they were never supposed to cross. Heat becomes increasingly difficult to remove. Manufacturing tolerances shrink to astonishing levels. A tiny defect invisible to the human eye can ruin an entire wafer worth millions of dollars. This is one reason semiconductor fabrication has become one of the most expensive industries on Earth. Building a leading-edge fabrication plant now costs tens of billions of dollars. Every new manufacturing generation requires increasingly sophisticated equipment. Extreme ultraviolet lithography, atomic layer deposition, advanced packaging, high-precision metrology. Each improvement demands more investment while delivering smaller performance gains. Engineers sometimes describe this as the easy progress coming to an end. For decades, shrinking transistors solved nearly every problem. Today, shrinking them further solves fewer problems while creating entirely new ones. Artificial intelligence has made those limitations impossible to ignore. Modern AI models no longer rely on a single processor performing calculations independently. Instead, thousands of processors work together simultaneously. Each processor constantly exchanges enormous amounts of information with every other processor. That communication consumes time. It consumes electricity. It generates heat. And increasingly, it limits overall system performance. Ironically, some of the world's most powerful AI processors now spend part of their time waiting. Not because they're too slow, because information can't reach them quickly enough. That's a remarkable reversal. For years, processors represented the bottleneck. Now the bottleneck often exists between the processors. Moving data has become almost as important as processing data. This shift explains why researchers are exploring technologies that don't simply improve silicon. They're trying to redesign the entire architecture surrounding it. China has become particularly active in this area. Over the past several years, we've seen Chinese researchers publish advances involving photonic chips capable of transmitting information using light rather than electrical signals. Glass-based packaging technologies designed to improve chip communication. Air-filled optical fibers capable of transmitting enormous amounts of data across impressive distances. Novel semiconductor materials intended to reduce energy loss. Optical interconnects designed specifically for AI infrastructure. Advanced chip packaging that shortens communication pathways. Viewed separately, each breakthrough appears highly specialized. Viewed together, they reveal a consistent strategy. Instead of asking how to build a slightly faster processor, researchers are asking how to eliminate the limitations surrounding today's processors altogether. That's an important difference. Imagine upgrading the engine inside a race car while leaving narrow tires, weak brakes, and poor suspension unchanged. The engine becomes more powerful. The car doesn't necessarily become much faster. Modern AI faces a similar challenge. Processors have advanced rapidly. Memory has improved. Storage has become dramatically faster. But communication between all those components hasn't improved at the same pace. That imbalance has created entirely new engineering priorities. This helps explain why many semiconductor conferences today focus as much on packaging, networking, photonics, and material science as they do on transistor density. The future isn't being defined by one component. It's being defined by how every component works together. China's semiconductor strategy appears increasingly aligned with that philosophy. Rather than concentrating every investment on traditional silicon scaling, the country has expanded research across multiple complementary fields: advanced materials, optical communication, AI networking, memory technology, chip packaging, photonics, integrated manufacturing. Each area addresses a different weakness inside conventional computing. Individually, none replaces silicon. Collectively, they reduce dependence on silicon doing everything alone. That's why the title of this video isn't suggesting silicon suddenly disappears tomorrow. It suggests something arguably more significant. Silicon may no longer be the only foundation capable of supporting next-generation computing. Future AI systems may rely on entirely new combinations of technologies working alongside traditional semiconductor designs. Processors optimized for specific workloads, photonic communication replacing electrical signaling, advanced packaging reducing communication distances, novel materials handling specialized calculations, silicon remaining where it performs best. This hybrid approach could extend computing far beyond what conventional transistor scaling alone can achieve. Some researchers even argue that the future of computing won't belong to a single revolutionary material. Instead, it will belong to ecosystems capable of combining multiple technologies into one highly efficient platform. That possibility is attracting enormous investment worldwide, because whoever successfully builds that platform may define the next era of computing, not by making silicon slightly better, but by making the entire system fundamentally smarter. If silicon is approaching practical limits, the obvious question becomes surprisingly simple. What exactly replaces it? The answer is more complicated than many headlines suggest. There probably won't be a single material that suddenly takes over the semiconductor industry overnight. Instead, engineers increasingly believe the next generation of computing will emerge from several technologies working together, each solving a different problem that silicon struggles to handle. In many ways, the future of computing may look less like a replacement and more like an evolution. That's where China's recent research becomes particularly interesting. Rather than betting everything on one breakthrough, Chinese laboratories have been exploring multiple paths simultaneously. One of the most promising involves photonic computing. Traditional processors move information using electrons flowing through microscopic circuits. Photonic systems replace some of those electrical signals with light. At first glance, that may not sound revolutionary, but light behaves very differently from electricity. Photons travel at incredible speeds. They generate far less heat while transmitting information. They experience minimal electrical interference. And perhaps most importantly, they can carry enormous amounts of data simultaneously through optical pathways. These advantages become especially valuable inside artificial intelligence infrastructure. Modern AI isn't limited by mathematical calculations alone. It's limited by communication. Thousands of processors constantly exchange data. Memory modules feed enormous datasets into GPU clusters. Networking hardware moves information between racks. Storage systems continuously deliver new training data. Every delay reduces efficiency. If light can move that information faster than electricity, AI systems become more productive without necessarily building faster processors. That's one reason photonic technologies have become one of the semiconductor industry's hottest research areas. China isn't alone in pursuing this vision. Companies and research institutions across the United States, Europe, Japan, South Korea, and Taiwan are investing heavily in optical computing as well. But China's pace of announcements has accelerated noticeably over the past few years. We've covered breakthroughs involving photonic processors, glass-based chip packaging, air-filled fiber capable of record-breaking transmission speeds, optical interconnects, integrated AI networking. Each project addresses a different communication challenge. Together, they point toward a future where electrical signaling no longer carries every piece of information inside advanced computers. Another promising direction involves entirely new semiconductor materials. For decades, silicon dominated because it balanced cost, reliability, and manufacturing simplicity. But other materials possess electrical properties that outperform silicon in specific applications. Gallium nitride allows higher power efficiency. Silicon carbide excels in electric vehicles and industrial power electronics. Two-dimensional materials measured only atoms thick are being explored for future transistor designs. Researchers are investigating carbon-based structures with remarkable electrical behavior. None of these materials completely replaces silicon today. Instead, each one solves particular problems where silicon reaches its limits. That's an important distinction. The semiconductor industry rarely abandons successful technology immediately. It gradually introduces specialized alternatives where the benefits justify the cost. We've already seen this happen in memory. Traditional hard drives still exist. Solid-state storage expanded alongside them. Cloud storage joined both. Each technology found its own role. The same pattern may emerge with computing materials. Silicon remains excellent for general-purpose processing. Photonics may dominate communication. Wide bandgap materials may power electric infrastructure. Advanced packaging may reduce communication delays. Novel memory technologies may eliminate existing bottlenecks. Instead of replacing silicon entirely, future computers may simply rely on silicon much less than they do today. That shift could prove just as significant. China's strategy appears designed around exactly this kind of diversification. Rather than concentrating every research dollar on one revolutionary invention, investments span nearly every layer of modern computing. Semiconductor manufacturing, memory technology, advanced packaging, optical communication, artificial intelligence hardware, materials science, telecommunications, industrial automation. This creates something more valuable than isolated breakthroughs. It creates an ecosystem where improvements in one field immediately benefit another. Faster networking improves AI clusters. Better packaging enhances processor performance. Artificial intelligence has fundamentally changed what high-performance computing requires. Success no longer depends on processor speed alone. It depends on communication, power efficiency, heat management, memory bandwidth, packaging technology, networking architecture, manufacturing capability, software optimization, supply chains. The winners of tomorrow's computing industry will likely master all of them. That's why replacing silicon isn't really about one material defeating another. It's about building an entirely new generation of computing infrastructure. And if China's current strategy succeeds, the biggest breakthrough may not be a single revolutionary processor. It may be something much larger, a computing platform where silicon is no longer the star of the show. Instead, it becomes just one component inside a far more advanced technological ecosystem. Whether silicon is truly nearing the end of its dominance remains an open question. Predicting the future of technology has never been easy, especially in an industry that has repeatedly surprised even its own experts. Every few years, a breakthrough emerges that changes expectations, reshapes investment, and forces companies to rethink their long-term strategies. What's different today is the scale of that transformation. Artificial intelligence has accelerated demand for computing faster than almost anyone anticipated. Data centers continue growing larger. AI models require exponentially more processing power. Energy consumption keeps climbing. At the same time, the physical limits of traditional chip design are becoming increasingly difficult and expensive to overcome. That reality is pushing the entire industry to think differently. Instead of relying on one material to solve every problem, researchers are building systems where multiple technologies work together. Silicon may continue handling general-purpose computing, while photonics speeds up communication, advanced materials improve efficiency, and new packaging techniques reduce delays between components. In many ways, the future may not belong to a single revolutionary invention. It may belong to whoever integrates these technologies into one seamless platform first. China appears determined to compete in exactly that race. Over the past several years, we've seen growing investment across semiconductor manufacturing, AI hardware, optical networking, advanced materials, memory technologies, and chip packaging. Each announcement on its own may seem incremental, but together they suggest a broader strategy, one focused on shaping the next era of computing rather than simply catching up to the last one. Of course, none of this means silicon suddenly becomes obsolete tomorrow. Billions of devices around the world will continue relying on silicon for many years to come. The semiconductor industry doesn't replace foundational technology overnight. It evolves step by step, generation by generation. But history shows that every technological era eventually reaches a turning point. Vacuum tubes gave way to transistors. Mainframes gave way to personal computers. CPUs were joined by GPUs. Now, the industry is searching for what comes after today's AI hardware. Whether the next breakthrough comes from photonics, new semiconductor materials, hybrid architectures, or an approach nobody has imagined yet, one thing is becoming increasingly clear. The future of computing will likely look very different from the systems we've relied on for the past 50 years. And if that future arrives sooner than expected, today's biggest advantage may not belong to the company with the fastest silicon chip. It may belong to the country that successfully builds what comes next. If you enjoyed this video, don't forget to like, subscribe and turn on notifications so you never miss our latest deep dives into AI, semiconductors, and the technologies shaping the future. Thanks for watching, and I'll see you in the next one. Turn off a computer, and something strange happens. The files on the SSD remain exactly where they were, but everything held inside RAM disappears. Open documents, active calculations, temporary AI data, the precise state of every running program, all of it vanishes the moment electrical power is removed. That is the basic compromise inside nearly every modern computer. Fast memory forgets. Memory that remembers is slower. But researchers at Fudan University in Shanghai have built a device that appears to challenge that division. Their experimental flash memory stored information without continuous power, survived more than 5.5 million write cycles, and completed a programming operation in just 400 picoseconds. A picosecond is 1/trillionth of a second. At that speed, the device can theoretically complete 2.5 billion programming events in 1 second. Compared with conventional flash memory, whose programming time is often measured in tens of microseconds, the difference can approach 100,000 times. And the researchers say their device can program faster than SRAM built with the same channel length. That sounds like the beginning of universal memory. One technology combining the speed of working memory with the persistence of storage. But this is not yet a commercial RAM replacement. It is not a terabyte SSD. And the 400 picosecond result came from a tiny experimental device under carefully controlled conditions. The real breakthrough is more fundamental. For decades, engineers assumed that flash memory could not cross the 1 nanosecond barrier because its method of storing charge was simply too slow. Fudan's team crossed it. Then, months later, the same researchers integrated their two-dimensional memory technology with conventional silicon electronics and created a functional flash chip. The first experiment proved the physics. The second showed a possible path toward actual hardware. Together, they raise a much larger question. What happens if computers no longer have to choose between speed and memory that survives when the power goes out? The chalkboard and the stone tablet. A computer's memory system is not one single pool. It is a hierarchy. At the top are tiny registers inside the processor. They are extraordinarily fast, but there are very few of them. Below that is cache, followed by system RAM. These layers hold data close to the processor so calculations can happen quickly. Farther away sits persistent storage, SSDs and hard drives. Storage provides far more capacity, but the processor must wait longer to reach it. The arrangement exists because no single memory technology delivers every desirable property at once. SRAM is extremely fast, but it takes a large amount of silicon area and loses information without power. DRAM is denser and cheaper, but it must constantly refresh its electrical charge and also forgets when powered down. NAND flash stores enormous quantities of data and remembers without electricity, but writing to it is dramatically slower. Think of RAM as a chalkboard. Writing is immediate, erasing is easy, but when the lights go out and the room is cleaned, the information disappears. Flash memory is closer to carving a message into a stone tablet. The inscription remains. The problem is that carving takes time. Fudan's POX device is an attempt to write on the stone tablet at chalkboard speed. Why normal flash is slow. Flash memory stores information by trapping electrical charge inside an insulated layer. The presence or absence of that charge changes how the memory cell behaves electrically, allowing the device to represent zeros and ones. The charge must cross an energy barrier to enter the storage region. In conventional flash, this commonly happens through tunneling or hot carrier injection. Both methods work. Neither is naturally instantaneous. In Fowler-Nordheim tunneling, a strong electric field encourages electrons to pass through an insulating barrier that they would not normally cross. The effect is reliable, but moving enough charge takes time and often requires relatively high voltage. Hot carrier injection takes another route. Electrons accelerate along the memory channel. Some gain enough energy to jump into the storage layer. The faster and more efficiently those carriers are accelerated, the faster the memory can be programmed. Silicon places practical limits on that acceleration. The electric field is not distributed perfectly, and only a small percentage of carriers become energetic enough to cross the barrier. Engineers have improved flash memory for decades through better materials, thinner structures, and more sophisticated control. But the underlying mechanism remains slow compared with volatile memory. The accepted assumption was simple. Flash could become denser, it could become cheaper, it could consume less standby power. But sub-nanosecond programming was beyond its natural limit. The Fudan researchers attacked that limit by changing the channel material itself. The graphene channel. The experimental memory uses graphene as its channel. Graphene is a sheet of carbon only one atom thick. Its electrons behave differently from those moving through ordinary silicon. Under the right conditions, they can travel with very high mobility and experience unusual energy relationships associated with what physicists call a Dirac material. The important feature here is not simply that graphene is thin, it is how that thinness changes the electric field inside the device. In a conventional silicon channel, the horizontal electric field used to accelerate carriers is distributed across a thicker body. In the two-dimensional channel, the field becomes more concentrated. The carriers accelerate more effectively. More of them reach the high-energy state needed to enter the storage layer. The researchers call this two-dimensional enhanced hot carrier injection. Imagine two ramps reaching the same wall. The first ramp is long and shallow. A rolling ball gains speed gradually, but friction removes much of the energy before it reaches the top. The second ramp is shorter and steeper. The ball accelerates more aggressively and reaches the barrier with far greater energy. The graphene channel creates something closer to the second ramp. The result was a much larger injection current than the researchers observed in a comparable silicon system. More charge entered the storage region in less time. That is what enabled the 400 picosecond programming pulse. What 400 picoseconds means? 400 picoseconds equals 0.4 nanoseconds. Light travels only about 12 centimeters in that amount of time. A modern processor running at 5 GHz completes one clock cycle every 200 picoseconds. So the POX programming operation occurred within roughly 2 processor clock cycles at that frequency. That is an astonishing figure for non-volatile flash memory. Conventional silicon flash can require 10 to 100 microseconds to program a cell. 10 microseconds divided by 400 picoseconds is 25,000. 100 microseconds divided by 400 picoseconds is 250,000. That is why describing the breakthrough as approximately 100,000 times faster is reasonable. But it is not one fixed multiplier for every existing flash technology. The comparison depends on the specific device, operating conditions, and definition of programming time. The researchers tested a graphene device with a channel length of 0.2 micrometers and a programming voltage of around 5 volts. They repeated the short pulse measurement and observed a stable memory response. They also demonstrated a related device using tungsten diselenide, another two-dimensional material, which achieved 1 nanosecond programming through hot hole injection. This suggests the mechanism is not limited to one isolated graphene sample. Different two-dimensional materials may support different versions of the same general approach. Never forgets needs context. The device does not literally remember forever. No physical storage medium does. Never forgets means the information remains when electrical power is removed. That makes it non-volatile. SRAM and DRAM require continuous power to preserve their states. Remove the voltage and the stored information disappears almost immediately. Flash traps charge inside an insulated region, allowing the state to survive. The Fudan device maintained a measurable non-volatile memory window, after programming and demonstrated endurance beyond 5.5 million cycles. That is important because speed alone would not make a useful memory. A device that writes in 400 picoseconds but fails after a few operations is a laboratory curiosity. A device that performs millions of cycles begins to look more credible. However, endurance testing on a small research device is not the same as proving reliability across billions of cells operating for years inside consumer hardware. Commercial memory must survive temperature changes, manufacturing variations, electrical noise, and repeated operation across a complete chip. The prototype established that the mechanism can be fast and repeatable. It did not complete the industrial journey. Why AI cares about this? Modern processors are becoming faster than the systems feeding them. This is known as the memory wall. An AI accelerator may contain thousands of arithmetic units capable of performing enormous numbers of calculations. But those units need model weights, activations, and intermediate results. If data arrives too slowly, the accelerator waits. The chip may be powerful enough to perform the operation. The memory system prevents it from starting. Moving data also consumes energy. In many AI workloads, transporting values between storage, DRAM, and the processor can use more energy than the calculation itself. That is why high-bandwidth memory has become so valuable. It places large amounts of fast memory extremely close to AI processors. But HBM is expensive, complicated to package, and still volatile. Every time a system starts, model data must be loaded from persistent storage into fast memory. Imagine a library that burns every book each night and reconstructs the collection every morning from a warehouse. The readers eventually receive the information. The rebuilding process wastes time and energy. A fast, non-volatile memory could preserve important data close to the processor even after shutdown. AI models might start more quickly. Edge devices could retain local model states without constantly refreshing memory. Computers could reduce the amount of data copied repeatedly between storage and working memory. This is the larger promise behind ultra-fast persistent memory. Could it replace RAM? Not today. The prototype demonstrated exceptional programming speed in an individual memory structure. A complete RAM system requires much more. Billions of cells must be arranged into dense arrays. Every cell must be selected without accidentally disturbing its neighbors. Read and write circuits must operate quickly. Manufacturing yield must be high. The chip must fit existing processor and memory interfaces. Cost per bit must compete with technologies produced in enormous factories. Latency also includes more than the programming pulse. A real computer must send an address, select the correct cell, move signals through wires, sense the stored state, correct errors, and transfer the result to the processor. A 400 picosecond device operation does not mean a future memory module will automatically deliver 400 picosecond system latency. The difference resembles a car engine capable of reaching a certain rotational speed. That number matters. But the speed of the complete vehicle also depends on the transmission, tires, aerodynamics, and road. The experimental device proved the engine. The researchers still needed to build more of the car, and that is exactly what they attempted next. The second breakthrough. Later in 2025, the Fudan team reported a full-featured two-dimensional NOR flash memory chip integrated with conventional silicon CMOS electronics. This was a major step beyond the original device demonstration. The new chip used the two-dimensional material as the memory core while mature silicon circuitry handled instruction control and system operation. The researchers called the integration method ATOM2CHIP. The chip supported random access, 8-bit instruction operations, and 32-bit parallel operation. Full chip testing produced a reported memory cell yield of 94.34%. Its integrated memory cells operated in 20 nanoseconds and consumed as little as 0.644 picojoules per bit. 20 nanoseconds is far slower than the original 400 picosecond pulse. That does not mean the later chip failed. It means integration introduces real-world overhead. The signal must pass through control circuits. Cells must be addressed. Operations must occur across an array rather than one optimized test device. The integrated chip sacrificed record-setting speed in exchange for functionality. That is often how new technology develops. The first prototype demonstrates an extreme physical result. The first system trades some of that result for reliability, control, and manufacturability. 20 nanoseconds is still fast for non-volatile flash memory. More importantly, the researchers showed that the two-dimensional memory could communicate with a conventional CMOS platform. Why integration is so difficult? Two-dimensional materials can be only one or a few atoms thick. That creates remarkable electrical properties. It also makes manufacturing difficult. A conventional silicon chip surface may look perfectly smooth to the human eye. At atomic scale, it resembles rough terrain. Different structures rise from the surface. Metal lines, insulating regions, and contacts create tiny height variations. Placing an atomically thin layer directly across that surface is like stretching plastic film over an entire city. From an airplane, the land looks flat. At street level, buildings, bridges, and towers make a smooth covering impossible. The film can wrinkle, tear, lose electrical performance, or fail to contact the correct region. The Fudan team's solution was modular. They manufactured the two-dimensional memory section and conventional CMOS control circuitry separately, then connected them through dense vertical interconnects. This allowed the new material to preserve its performance without requiring the entire silicon surface to become atomically flat. The approach also avoids rebuilding every part of the computer from experimental materials. Conventional CMOS remains excellent at logic. The two-dimensional layer performs the memory function, where its unusual physics provides the greatest advantage. This hybrid strategy may be more realistic than attempting to replace silicon completely. NOR flash versus the SSD in your computer. The integrated chip was a form of NOR flash. That distinction matters. Most large SSDs use NAND flash. NAND is optimized for extremely high density and low cost per bit. It arranges cells in long strings and reads or writes data in larger blocks. NOR flash offers direct random access and is commonly used for firmware and code storage, where rapid, precise access matters more than maximum capacity. The Fudan device therefore should not be imagined as an immediate replacement for a multi-terabyte NAND SSD. Its potential may first appear in applications requiring fast persistent access, processor boot code, AI accelerator configuration, embedded systems, automotive electronics, edge computing devices, persistent cache, memory placed close to specialized processors. These markets may tolerate higher cost per bit if the technology reduces startup time and energy consumption. Only after manufacturing improves could the concept challenge larger portions of the memory hierarchy. The dream of universal memory. Engineers have pursued universal memory for decades. The ideal technology would combine 5 properties: SRAM-like speed, DRAM-like density, flash-like persistence, low energy consumption, and nearly unlimited endurance. No existing memory provides all 5. Phase change memory retains data and can be fast, but heat and material changes create challenges. Magnetic memory offers strong endurance, but scaling and density remain difficult. Resistive memory can switch quickly, yet device-to-device variation complicates large arrays. Ferroelectric memory is promising, but integration and long-term reliability remain active engineering problems. POX adds another candidate. Its unusual advantage is that it remains a charge storage device related to flash, but changes the injection mechanism using 2-dimensional materials. That connection to familiar flash principles could help engineers understand and adapt the technology. Still, universal is an extremely demanding word. A memory can be fast but too expensive, persistent but insufficiently dense, efficient but difficult to manufacture. The winner will not be determined by one record. It will be determined by which technology can survive a factory. What still has to happen? The first challenge is scale. The research team must move from small arrays to millions and eventually billions of memory cells. Yield becomes harder as the array grows. A 94% yield sounds strong for an early research chip. For mass production, even a small defective percentage can become unacceptable when billions of cells are involved. The second challenge is uniformity. Atomically thin materials must behave consistently across large wafers. A small difference in thickness, contamination, or contact resistance can change device performance. The third challenge is density. The memory must store enough bits per unit area to justify its cost. The fourth challenge is voltage. The prototype used programming voltages around 5 volts. Future systems may need lower operating voltage to reduce power and simplify integration. The fifth challenge is economics. Graphene and other 2-dimensional materials must be deposited, patterned, and connected using processes compatible with high-volume semiconductor manufacturing. A technology can outperform existing memory and still lose if each chip costs 10 times more. The final challenge is time. The researchers have discussed expanding toward much larger integration within several years. That is ambitious. Even successful semiconductor technologies can require a decade or more to move from laboratory demonstration to widespread commercial use. My take. My view is that the most important result is not the 100,000 times headline. The speed is spectacular. But research laboratories produce spectacular isolated numbers regularly. What makes this story different is the sequence. First, the team demonstrated a 400 picosecond non-volatile flash device. Then it built a functional hybrid chip around the same broader 2-dimensional memory concept. The system was slower than the record prototype, but it could execute instructions, perform parallel operations, and access memory randomly. That is progress in the correct direction. The first result said, the physical speed limit can be broken. The second said, the device can begin participating in a real circuit. China has not eliminated RAM. It has not produced a commercial universal memory chip. And no laptop shipping today contains POX memory. But the traditional boundary between fast volatile memory and slow persistent storage looks less permanent than it did before. For most of computing history, the rule was simple. Anything fast enough to serve the processor forgot when power disappeared. Anything that remembered was forced into a slower tier. The Fudan experiments show that this rule is not fundamental. It is a consequence of the materials and device structures we currently use. Change the material, reshape the electric field, accelerate the carriers differently, and flash memory can enter a speed range that once appeared impossible. The hardest work begins now: scaling, manufacturing, reducing voltage, improving yield, and proving that the technology can remain reliable outside a research laboratory. But every commercial memory technology began with a device that looked too small, too unusual, or too expensive to matter. The question is whether POX follows the same path or remains a brilliant record in a scientific paper. So what do you think? Could ultra-fast non-volatile memory eventually replace both RAM and flash with one universal technology? Or will manufacturing cost and scaling challenges keep the computer's memory hierarchy intact? Let me know your view in the comments. And if you want more grounded stories about the chips, materials, and hidden engineering breakthroughs reshaping computing, subscribe to Eastern Engine, because the next revolution in memory may not be a drive with more capacity, it may be a chip that refuses to forget. In 1972, an American astronaut climbed back into his lunar module, took one last look at the gray horizon, and left the moon behind. That was the last time any human stood on the surface of another world, 50-some years ago. And ever since, going back has been something the world's biggest space powers have talked about far more than they've actually done. But here's the thing, almost nobody outside the space world is paying attention to. While America's return to the moon keeps slipping, one delay, then another, China has quietly set a date, 2030, and it is hitting its checkpoints one by one, almost exactly on schedule. So the question is no longer whether humans will walk on the moon again, it's who gets there next, and whose flag is planted when they do. Today, let's look at exactly how close China really is, why NASA is genuinely nervous, and whether the country that's never sent a single person to the moon could actually beat the country that's already done it 6 times. Let's start with what China is actually saying, because it would be easy to wave this off as the kind of grand announcement countries love to make and then never follow through on. China's Manned Space Agency has stated, plainly and repeatedly, that it intends to land astronauts on the moon before the year 2030. And recently, officials doubled down, saying the program is on track and that the hardware is, in their words, progressing smoothly. Now, talk is cheap. Plenty of moon promises have come and gone. What makes this one different is that China has spent the last 2 decades building a track record that's almost boringly reliable. They say they'll do a thing, set a date, and then, more often than not, they do it. Consider what they've already pulled off. They've landed robotic missions on the far side of the moon, the side that always faces away from Earth, which no other country had ever soft landed on. They've scooped up lunar soil and flown it back to Earth. They've built and fully staffed their own space station, orbiting right now with crews rotating in and out. This is not a country fumbling towards space. This is a country that has been methodically climbing a ladder, rung by rung, and the top of that ladder is a human footprint on the moon. So what does it actually take to put people on the moon? 3 big pieces of hardware, and China is building all 3 at once. First, the rocket. It's called the Long March 10, a giant 3-stage heavy-lift rocket designed specifically to throw enough mass toward the moon to make a crewed landing possible. Building a rocket this powerful is one of the hardest things any space program can attempt, and only a handful of nations have ever managed it. To put it in perspective, getting a crew to the moon and back isn't like launching a satellite into orbit a few hundred miles up. You have to push a heavy spacecraft nearly 250,000 miles, slow it down, and then have enough power left to bring everyone home. That demands raw muscle that very few rockets in history have ever had, and China is building theirs from the ground up. What's interesting is the approach they've taken. Rather than inventing something wildly experimental, they've scaled up and refined technology they already trust, clustering proven engines together to generate enormous thrust. It's a conservative, methodical design philosophy. And in spaceflight, conservative and methodical is often exactly what gets you to the finish line in one piece. Flashy doesn't matter on the launch pad. Reliable does. Second, the crew spacecraft. It's named Mengzhou. Think of it as China's version of the capsule that carries astronauts out to the moon and safely back home. It's built in 2 parts, one section that brings the crew back to Earth, and another that provides power, propulsion, and life support along the way. It's designed to carry a crew of around 6, which is notable on its own, because more seats means more capability, more scientists, more equipment, more ambition per mission. And critically, parts of it are being designed to be reusable, which is a sign China is thinking past a single heroic landing and toward a sustained program of going back again and again. This capsule has to do something genuinely difficult too. Coming home from the moon, a spacecraft slams into Earth's atmosphere far faster than anything returning from low orbit. We're talking a fiery, high-speed re-entry that demands a heat shield and a guidance system that simply cannot fail. The fact that China is already flight testing this hardware, rather than just sketching it on paper, tells you how far along they really are. And third, the lander itself, named Lanyue, which translates beautifully to embracing the moon. This is the vehicle that would actually carry astronauts down to the surface and back up to lunar orbit. It's reportedly capable of bringing along a small rover, so the crew wouldn't just plant a flag and leave. They'd actually drive across the surface and explore. Think about what that signals. A flag and footprints mission is a photo op. A mission that brings a rover is the beginning of real exploration, covering ground, studying the terrain, scouting for resources. China isn't designing a quick visit, they're designing a foothold. Here's the part that should make you sit up. China says testing on the lander began back in 2024. The crew capsule is already going through prototype flights, and they've laid out a clear sequence: robotic test flights first, then uncrewed system tests, then a joint test mission near the end of the decade, with the crewed landing a year after that. Every piece has a slot on the calendar. They've even talked publicly about testing the emergency escape systems, the hardware that would yank a crew to safety if a launch went wrong, which is the kind of unglamorous safety-first detail that serious programs obsess over and pretenders skip. It's a staircase, and so far, they're walking up it on time. Now, let's talk about the other side of this race, because you can't understand why people are nervous without it. America's plan to return to the moon is called Artemis. And to be clear, Artemis is real, it's serious, and it has made genuine progress. NASA has flown crews around the moon for the first time in 50 years. The ambition is enormous, not just to visit, but to build a lasting presence. A stepping stone towards sending humans all the way to Mars. But Artemis has one persistent problem: delays. The timeline has slipped again and again. A mission that was once aimed at 1 year got pushed to the next, and then the next. At one point, NASA restructured the program entirely, adding an extra test flight before the actual landing, which pushed the boots on the moon moment even further out. The program has run years behind its original schedule and tens of billions of dollars over budget. And it's worth being fair about why these delays happen, because it's not simple incompetence. Part of it is that NASA holds itself to an extraordinarily high safety bar. These are human lives, and the agency carries the memory of past tragedies. Part of it is that the program depends on a web of contractors and commercial partners, each with their own timelines and technical hurdles. And part of it is politics. Budgets shift, administrations change, priorities get rewritten every few years. America's space program has to survive a gauntlet that China's, run by a single centralized state, simply doesn't face in the same way. But the reasons for the delays don't change the result of the delays. And this is where the math gets uncomfortable. On paper, America is still aiming to land first. NASA's leadership has said publicly they intend to be on the surface before China is. But on paper is doing a lot of work in that sentence. Because every time Artemis slips, the gap between America's target and China's 2030 deadline gets thinner. A program that's ahead but keeps sliding backward is, at some point, just a program that's running out of cushion. It's like watching two runners. One has a head start and far more experience, but that runner keeps stopping to retie their shoes, while the other is running at a steady, relentless pace and never breaks stride. The runner in front is still in front, for now, but anyone watching can feel which way the momentum is flowing. So why does this rattle people in Washington? Why not just shrug and say, "We've been to the moon, we'll get there again"? Because in this race, second place has consequences that go way beyond bragging rights. Members of the US Congress have openly warned that the country cannot afford to let China reach the moon first. NASA's own leadership has framed this as a great competition with a rival that has both the will and the means to challenge America in space. Those are not casual words. That's the language of a country that has realized it might actually lose something it assumed it owned. And here's the strategic twist that makes this more than a symbolic contest. Both China and America are aiming for the same destination, the moon's south pole. Why there? Because scientists believe those permanently shadowed craters hold water ice. And water on the moon is everything. You can drink it, you can split it into oxygen to breathe, and into hydrogen for rocket fuel. In other words, whoever establishes a foothold at the lunar south pole first gets first pick of the most valuable real estate off of planet Earth. This isn't about a flag and a photo. It's about who sets the rules for the next era of space, who builds the first base, who controls the best landing sites, who writes the playbook everyone else has to follow. And there's a deeper layer here that's easy to miss. The first moon race, back in the 1960s, was about proving a point. A contest of ideologies between two superpowers settled the moment a boot hit the dust. This new race is different. It's not about a single symbolic moment, it's about staying. Both sides are talking about permanent bases, long-term presence, and using the moon as a launch pad for going even deeper into space, eventually to Mars. The moon, in this version of the story, isn't the finish line. It's the gas station, the outpost, the high ground. There's also a question of leadership that goes beyond the moon itself. Space achievement has always been a kind of global advertisement, a way of telling the rest of the world, look what our system can do. When a country lands humans on another world, it doesn't just win a scientific prize. It wins prestige, influence, and the ability to pull other nations into its orbit, sometimes literally, by inviting partners onto its missions and into its station. China has been openly courting international partners for its lunar ambitions. Every country that signs on with China is a country not signing on with America, and vice versa. The moon, in that sense, has become a stage where a much larger competition plays out. That's why a country that already won the moon race once is suddenly very, very focused on not coming in second the second time around. Now I want to show you the moment that, to me, really captures how serious China is, and most people scrolled right past it. Recently, China launched a fresh crew to its space station. Routine on the surface, but buried in the details was something remarkable. One of those crew members is expected to stay in orbit for roughly a year, the longest single human spaceflight in China's history. Why does that matter for the moon? Because going to the moon and building a presence there, around 68 orbital launches in 1 year, to more than 90 the next, and they're on track for more than 140 in a single year. That's the tempo of a country that has turned spaceflight into something closer to an assembly line, and a fast-moving one. When a space program is launching that often, testing that aggressively, and keeping people in orbit for a year at a time, it tells you something. They're not hoping to reach the moon. They're training for it. Let me zoom out for a second, because I think the single most important thing to understand about China's space program isn't any one rocket or capsule, it's the pattern. For decades, China's approach to space has followed the same quiet rhythm. Announce a clear goal, set a realistic date, build the pieces step by step, and let the results do the talking. No dramatic press conferences promising the impossible. No moonshots in the reckless sense of the word, just a long, patient climb. Look at how the space station came together. They didn't try to build it all at once. They launched a test lab, learned from it, then launched the real modules one at a time, until they had a fully functioning station with crews living aboard. Each step de-risked the next. By the time the hard part arrived, they'd already practiced most of it. The moon program is following that exact same template. Robotic landings came first, including on the far side, which nobody had ever done. Then sample returns, bringing actual lunar material back to Earth, proving they could get to the moon, operate on it, and come home. Now they're building the crude hardware, testing it piece by piece, with a joint rehearsal planned before the real thing. It's the same staircase, just taller. And this is what makes the 2030 target so credible. It's not a number someone picked out of the air to grab headlines. It sits at the top of a sequence that's already mostly built, with each lower step already proven. When a country tells you it'll do something in 5 years, the right question is, have they been doing the work for the last 15? In China's case, the answer is yes. That doesn't make success guaranteed, but it does mean this deadline deserves to be taken seriously, far more seriously than the West has tended to take it. All right, the big question, can China really beat America back to the moon? Let me be honest with you, because that's the whole point of this channel. Nobody knows for certain, and anyone who tells you they're 100% sure is selling something. China still has enormous work ahead. They've never flown a human anywhere near the moon. Every piece of their lunar hardware, the giant rocket, the deep space capsule, the lander, still has to be tested, flown and proven, all within a few short years. That is a brutal timeline, and spaceflight has a long history of humbling anyone who gets cocky. One serious failure could push everything back. But, and this is the part that's hard to argue with, America's biggest enemy in this race might not be China at all. It might be America's own delays. If NASA holds its current schedule, it likely still lands first. If. And that little word has been the weak point in the Artemis program from the beginning. So here's the real shape of it. America is ahead, but stumbling. China is behind, but sprinting at a steady, disciplined pace. And when you've got one side losing momentum and the other gaining it, the gap doesn't just shrink, it can close all at once. Here's my honest opinion. For whatever it's worth, I don't think this comes down to who has the better engineers, because both sides are extraordinary at what they do. I think it comes down to consistency. China's superpower in this race isn't a magic piece of technology. It's that they pick a date, build the staircase, and climb it without drama. America has more raw capability and more experience, but it keeps tripping over its own budgets, politics, and shifting priorities. And if I'm being straight with you, I think the safe bet is not that China definitely lands first, but that this race is going to be far, far closer than most people in the West assume. The comfortable belief that America obviously wins, because it won before, That assumption is exactly what makes a country slow down, and slowing down in a race this tight is the most dangerous thing you can do. Whoever gets there first, one thing is certain, a new era on the moon is coming this decade. And for the first time since Apollo, it genuinely won't be a one-horse race. So now I want to hear from you. Do you think China actually pulls it off and lands on the moon by 2030? Or does America's experience win out in the end? And honestly, does it even matter to you who gets there first, as long as humanity goes back? Drop your answer in the comments. I read them. And the best takes sometimes become whole videos of their own. And if you want to keep up with this race, and everything else happening in China's technology, economy, and space programs as it unfolds, hit that subscribe button and ring the bell. This is Eastern Engine, where we break down the forces shaping the future, clearly and without the hype. New videos regularly, so you'll never miss what's coming next. Thanks for watching. I'll see you in the next one.
So Apple looking for relief from the chip crunch behind this week's Mac and iPad price hikes. And I'm told by a person briefed on the discussions, that includes asking the administration for more flexibility to work with Chinese memory suppliers. And of course follows CEO Tim Cook telling the Journal just last week that all vendor options are back on the table. Now the two key names in question are YMTC and CXMT, China's heavily state-backed domestic memory players. YMTC makes NAND flash storage, CXMT makes DRAM, the working memory.
China's largest memory chip maker has reportedly secured a deal worth nearly $3 billion from Tencent, one of the biggest technology companies in the country. Just days after reports said Apple was asking Washington for political clearance to buy memory from the same Chinese supplier, Changshin Memory Technologies, better known as CXMT, has landed what may be the strongest commercial endorsement in its history. The reported agreement covers more than 20 billion yuan, or roughly $2.94 billion, in DRAM chips for Tencent servers over several years. That memory will support cloud computing, databases, and artificial intelligence workloads. CXMT is no longer being treated only as a protected domestic challenger. It is becoming a supplier that major Chinese technology companies may be willing to depend on at enormous scale. If Tencent is prepared to commit billions of dollars to CXMT, could Apple be next? It is a story about how the global memory shortage, the AI infrastructure boom, and political pressure are rewriting the semiconductor supply chain. For decades, the DRAM market has been dominated by three companies. Samsung Electronics, SK Hynix, and Micron control most global production. That concentration gave them enormous influence over pricing, technology, and supply. When demand rises faster than new factories can respond, there are very few alternative suppliers capable of filling the gap. AI data centers are consuming huge amounts of advanced memory. Large models need memory close to processors so data can move quickly enough to keep expensive computing systems busy. Cloud companies also require conventional server DRAM for databases, virtualization, storage systems, and general computing. High bandwidth memory receives most of the attention because it sits beside advanced AI accelerators. And when the biggest technology companies build infrastructure at the same time, demand spreads across the entire market. According to the latest reporting, DRAM contract prices rose roughly 95% quarter over quarter during the first quarter of 2026.
Used in iPhones, PCs, and servers. Both are young companies compared with Samsung, SK Hynix, and Micron, which built their businesses decades ago. But they are gaining share quickly. Counterpoint says YMTC now has 13% of the global NAND market, while CXMT has 8% of DRAM. CXMT also gaining ground fast, preparing for what could be mainland China's largest IPO in years. And Counterpoint is hearing from stakeholders in the supply chain that these Chinese memory names can
Large cloud companies do not want to enter every quarter uncertain about price, availability, or delivery. And in some cases, they are willing to provide prepayments or commit years in advance to secure supply. The reported CXMT agreement may run for 3 years, while another source suggested it could extend as long as 5. That means Tencent is not simply making a spot purchase to cover a temporary shortage. DRAM is one of the most difficult semiconductor businesses to enter. The product may look simple compared with a central processor or graphics chip, but manufacturing it profitably requires extraordinary precision. A memory producer must create billions of microscopic cells that store data reliably. Those cells must work at high speed, consume little power, survive repeated use, and maintain consistency across huge production volumes. That increases cost and makes it difficult to compete with established companies that have spent decades refining their processes. Its early products were aimed mainly at China's domestic market, and many international customers had little reason to take the company seriously. A company does not need to be the global technology leader to become strategically important. It only needs to offer acceptable products, meaningful capacity, and a willingness to sign contracts when other suppliers are constrained. The company reportedly held about 7.7% of the global DRAM market in 2025, making it the fourth largest producer. In a tight market, even a single-digit share can influence prices and customer negotiations. It currently operates major 12-inch DRAM fabrication plants in Hefei and Beijing, with combined output estimated at around 300,000 wafers per month. New facilities and additional expansion could eventually double that figure to approximately 600,000 wafers per month. The company is also developing operations in Shanghai, including DRAM production and high-bandwidth memory packaging. But Tencent's reported commitment gives CXMT something extremely valuable: demand visibility. It can help a manufacturer plan equipment purchases, staffing, material supply, and future process development. CXMT received approval in May for an initial public offering on Shanghai's Star Market. The company reportedly aims to raise 29.5 billion yuan. Investors want proof that growth is not based only on policy support or optimistic forecasts, and they want evidence that the company's products are important enough for large buyers to sign long-term commitments. Major Chinese technology companies are trying to reduce their exposure to foreign supply restrictions. Tencent, Alibaba, ByteDance, Lenovo, Xiaomi, and other firms all depend on semiconductors produced or controlled by companies outside mainland China. Export controls have already restricted China's access to advanced AI accelerators and semiconductor manufacturing equipment.
Undercut incumbent suppliers by up to 30% depending on the contract. Now, Apple, it's been here before. 4 years ago, the company explored using YMTC chips in China-sold iPhones, then retreated under pressure from Washington. But the shortage is more severe now, and Apple has a lot less leverage with its traditional suppliers. That's why more tech companies are looking for alternatives. HP and Lenovo are both reportedly pursuing Chinese memory as a way to diversify supply. But this is not a quick swap.
A cloud company cannot expand infrastructure if it cannot secure enough components. So Chinese technology firms have strong reasons to support a domestic supplier, even if that supplier remains behind the global leaders. This does not mean they will accept any product at any price. Large data center operators care about performance, failure rates, power consumption, compatibility, and total operating cost. Server memory must run continuously under heavy workloads. A defective module can create outages, corrupted data, or expensive maintenance. Tencent therefore has to believe that CXMT can meet a meaningful standard. That is why the reported agreement is more important than a symbolic government order. Tencent is not buying memory for a demonstration project. It needs chips for real servers supporting real customers. The contract could therefore become one of the strongest tests of CXMT's manufacturing discipline. Success would generate more than revenue. It would create operational data. Every shipment provides information about defect rates, system compatibility, thermal behavior, and long-term reliability. That feedback can help CXMT improve future products. Higher production volumes also allow engineers to identify recurring process problems and improve yield. Semiconductor manufacturing becomes more competitive through repetition. The more wafers a company processes, the more opportunities it has to learn. This is one reason large customers can accelerate a supplier's development. Tencent may be buying memory because it needs supply today, but the partnership could help create a stronger competitor tomorrow. That is where Samsung, SK Hynix, and Micron should pay attention. CXMT is not about to replace them. The established leaders remain ahead in manufacturing technology, scale, customer trust, and advanced products. They also dominate high-bandwidth memory, which currently delivers some of the strongest margins in the industry. CXMT still faces serious challenges. One reported problem is low yield on next-generation DDR5 products. That matters because DDR5 is increasingly important for modern servers and personal computers. A company can announce impressive specifications, but customers ultimately care about how many reliable chips can be produced at acceptable cost. If yield remains weak, expansion alone will not solve the problem. More factory capacity can simply produce more expensive defective wafers. CXMT must therefore improve technology while expanding volume. That is difficult, but the Tencent deal provides time and money. And if CXMT can use this period of high prices to improve yield, the competitive landscape could change. The memory industry is cyclical. Shortages produce high prices and heavy investment. High prices encourage companies to build more capacity. Eventually, supply catches up. Prices fall. Weak producers then struggle because memory becomes a commodity again. CXMT's challenge is to use the current upcycle to become efficient before the market turns. The company's recent financial performance shows how powerful the upcycle has been. Its first quarter revenue reportedly reached 50.8 billion yuan, an increase of about 700% from a year earlier. It also recorded a net profit of 25 billion yuan after reporting a loss in the previous year. Those numbers are extraordinary, but they should be interpreted carefully. A booming memory market can make almost every producer look stronger. The real test comes when prices normalize. Can CXMT still compete when buyers have more options? Can it maintain margins? Can it continue investing? And can it keep customers when Samsung, SK Hynix, and Micron have available capacity again? Tencent's long-term agreement may protect CXMT from some of that uncertainty. Now we come to Apple. Reports say Apple has been lobbying the United States government for clearance to purchase memory chips from CXMT. The request does not mean a contract has been signed. It does not mean CXMT memory is already inside MacBooks or iPads. And it does not mean Apple plans to abandon its current suppliers. Apple still depends on Samsung, SK Hynix, and Micron. But the company recently raised prices on several Mac and iPad models after memory and storage costs rose sharply.
Qualifying a new supplier can take months to as long as 2 years with device testing, reliability checks, factory audits, and technical sharing. And it's especially complicated with YMTC. It's been on the Commerce Entity List since 2022, meaning that U.S. companies need approval to share their blueprints and other proprietary details with them.
That makes another supplier extremely attractive. Apple does not need CXMT to replace the market leaders. It only needs CXMT to provide qualified products at meaningful volume. Even a limited supply agreement could strengthen Apple's negotiating position. It could reduce dependence on 3 dominant producers. And it could help Apple avoid even larger price increases if the shortage continues. The Tencent agreement may make CXMT easier for Apple to evaluate. A multi-billion-dollar server contract gives the company commercial credibility. It shows that another major technology buyer is willing to make a long-term commitment. But Apple's standards are different. For laptops and tablets, power consumption is critical. Memory affects battery life, heat, system stability, and product reliability. Apple also demands consistency across millions of devices. A supplier must deliver the same quality from one production batch to the next. It must support product launches, regional demand changes that allowing Apple to purchase from CXMT would strengthen a strategic Chinese semiconductor producer. They may also warn that Apple could become dependent on a supplier that Washington later restricts. Apple wants confidence before spending months qualifying products and redesigning logistics. A deal that is legal today could become impossible tomorrow. That uncertainty explains why Apple reportedly approached the government before moving forward. The White House has not publicly approved the request. Apple has not announced a supply agreement. And CXMT has not confirmed that it will supply Apple. So the title, Apple may be next, must remain a possibility, not a conclusion. Still, the Tencent deal changes the context. Before this agreement, CXMT could be described as a rising Chinese memory producer, seeking credibility. After a $3 billion commitment, it begins to look like a strategic supplier with major customers, rapid growth, expanding capacity, and access to capital. That does not guarantee Apple will follow, but it makes the possibility more believable. My take is that the most important part of this story is not the dollar amount. It is the speed at which CXMT's position is changing. A global shortage has turned capacity into leverage. AI demand has pushed memory from a commodity component into a strategic resource. Chinese technology companies are locking in domestic supply, and Apple is reportedly considering a supplier that would have seemed politically unrealistic only a short time ago. The old memory market was built around 3 dominant companies and predictable customer relationships. The new market is becoming more fragmented, more political, and more expensive. Tencent wants supply security. CXMT wants scale and validation. China wants semiconductor independence. Apple wants lower costs and another negotiating option. Washington wants to limit the growth of strategic Chinese technology. Those goals are now colliding inside one of the most basic components in modern computing. A small memory chip has become part of a much larger contest over AI, industrial power, and national security. The Tencent contract may prove that CXMT can serve China's largest technology companies. The Apple decision could determine whether it can cross into the supply chain of one of America's most influential corporations. So what do you think? Should Apple be allowed to buy memory from CXMT if the chips meet its technical standards? Or would that strengthen a Chinese semiconductor company at the expense of long-term American supply chain security? Let me know your view in the comments. And subscribe to Eastern Engine for more grounded coverage of the chips, factories, and engineering decisions reshaping the global economy. Because CXMT did not just win a $3 billion order. It may have won the credibility needed to compete for something even bigger. A normal solid-state drive has one job: store data. It receives files from the computer, places them inside flash memory cells, and returns them when requested. The controller organizes the traffic, corrects errors, and tries to keep the drive alive as thousands of writes gradually wear down the NAND. But a Chinese memory company believes the SSD should do much more than move data from one place to another. Longsys has introduced a 5-nanometer chip called the WM8500. The company describes it as an SPU, a storage processing unit. And according to Longsys, this chip can compress data inside the drive in real time, without requiring the host processor to handle the work. Across text, source code, databases, and similar workloads, the company reports an average compression ratio of approximately 2:1. That creates an extraordinary possibility. A drive containing 128 terabytes of physical flash could provide as much as 256 terabytes of effective storage. No additional NAND package, no second SSD, no magical new memory cell. The same physical drive simply stores certain data more efficiently. But capacity doubling is only the beginning. Longsys says the SPU can also move selected AI data out of expensive DRAM and into high-speed storage, reducing memory requirements by nearly 40% in one tested scenario. The company has even demonstrated a system built around AMD's Ryzen AI Max Plus 395, running a 397 billion parameter model locally. That sounds almost impossible for a compact machine. Yet the idea behind it is surprisingly simple. Instead of treating storage as a passive warehouse, Longsys wants the SSD to become an active participant in computing. The drive does not merely hold the data, it compresses it, sorts it, predicts when it will be needed, and in some cases, acts as an extension of system memory. If the technology works as described, the future SSD may not be measured only by how many terabytes it contains. It may be measured by how intelligently it uses every byte. The storage problem. AI created. For years, computer performance was discussed mainly in terms of processors. Faster CPU, faster GPU, more cores, higher clock speeds. But artificial intelligence has exposed a different bottleneck: memory. A large AI model may contain billions or hundreds of billions of parameters. Each parameter represents a numerical value learned during training. To run the model, those values must be stored somewhere and moved repeatedly into the processor. The calculations can be fast. Moving the data is often slower. Imagine owning a factory with thousands of extremely powerful machines. The machines can assemble products at incredible speed, but every component is stored in a warehouse several kilometers away. The machines spend less time working than waiting for deliveries. That is the AI memory problem. High-end data centers attack it with massive amounts of high-bandwidth memory, large pools of conventional DRAM, and extremely expensive storage systems. An ordinary PC cannot do that. Even a powerful workstation may have 64, 128, or 256 gigabytes of memory. A large model may require far more. So developers use a technique called offloading. Part of the model remains in fast DRAM. The rest is stored on an SSD and loaded only when needed. This makes larger models possible, but it introduces another problem. SSDs are much slower than DRAM. If the wrong data is requested at the wrong moment, the processor must wait. Longsys is trying to reduce that delay by making the drive itself more intelligent. From SSD controller to storage processor. Every SSD already contains a controller. The controller translates commands from the computer, decides where data should be written, manages bad memory cells, and performs error correction. Without it, NAND flash would be difficult to use reliably. But the traditional controller is largely a traffic manager. It moves data. The WM8500 is designed to process data too. Longsys says the SPU combines a conventional storage control engine with an intelligent processing engine on the same chip. That distinction matters. A normal controller asks, where should this file be placed? The SPU can ask additional questions. Can this file be compressed? Is it used frequently? Should it remain close to the processor? Can part of it be moved into a cheaper region of the drive? Will the system need it again soon? The company calls the software layer controlling these decisions ISA, or Intelligence Storage Agent. The SPU is the muscle. The ISA is the planner. Together, they turn the drive from a passive destination into something closer to a data assistant. The idea resembles what happened to graphics cards. A GPU was once a specialized component responsible mainly for drawing images. Over time, it became a general computing engine used for science, simulation, and artificial intelligence. Longsys is suggesting that storage controllers may follow a similar path, not by replacing CPUs or GPUs, by performing the data management work those processors should not have to do. How 128 terabytes becomes 256 terabytes. The headline number comes from lossless compression. Lossless means the original data can be reconstructed perfectly. Nothing is thrown away, nothing is blurred, nothing is approximated. A photograph saved as a low-quality image may use lossy compression, where some visual information is permanently removed. That can reduce file size dramatically, but the original cannot be recovered exactly. Lossless compression works differently. It searches for repeated patterns and replaces them with shorter instructions. Suppose a document contains the word semiconductor 10,000 times. Instead of storing every letter 10,000 times, a compression system can store the word once and then record where it repeats. The file becomes smaller. When it is read, the system reconstructs the full version. Longsys says the WM8500 performs this process directly inside the storage device. The computer sends data to the SSD. The SPU analyzes it. Compressible data is reduced before being written to flash. When requested, the SPU decompresses it before returning it to the host. To the operating system, the process can appear transparent. The user does not need to place files inside an archive manually. The drive handles it automatically. With an average 2-to-1 ratio on suitable workloads, 1 physical terabyte can store approximately 2 terabytes of original information. That is how 128 terabytes can provide up to 256 terabytes of effective capacity. But the phrase suitable workloads is essential. Not all data compresses equally. The files that refuse to shrink. Text compresses extremely well because language contains repetition. Source code also contains repeated words, structures, commands, and symbols. Databases may contain recurring values, empty fields, and predictable patterns. These are the kinds of workloads Longsys highlights. Video is different. Modern video files are already heavily compressed. A movie encoded with an efficient codec has already had most of its obvious redundancy removed. Trying to compress it again may save almost nothing. The same applies to JPEG photographs, compressed archives, and many encrypted files. Encryption deliberately makes data appear random. Random-looking data contains fewer predictable patterns for a compression engine to exploit. So a 128 terabytes drive will not always behave like a 256 terabytes drive. One user may see close to the full 2-to-1 benefit. Another may see only a small improvement. A data center filled with text logs, program code, and database records could benefit greatly. A media archive filled with compressed movies may not. This is not a flaw unique to Longsys. It is a basic limit of compression. You cannot repeatedly squeeze information forever. Eventually, the obvious repetition disappears. That is why the most honest description is not, Longsys created a physical 256 terabytes SSD. It created a 128 terabyte storage platform that may hold as much as 256 terabytes of uncompressed source data under favorable conditions. Still impressive, just not magic. Why put compression inside the drive? Computers have compressed files for decades. Operating systems can compress folders. Databases use compression. Servers use software tools to reduce storage needs. So why build dedicated compression hardware inside an SSD controller? Because compression requires computation. If the CPU performs it, processor time is consumed. Data must move through system memory, power is used. Other programs may slow down. A dedicated engine can perform the same task more efficiently. Think of a restaurant kitchen. The head chef can wash every plate personally. But that is probably not the best use of the most valuable worker in the building. A dedicated dishwasher handles the repetitive task while the chef focuses on cooking. The SPU attempts to do the same for data. The CPU and GPU focus on applications and AI calculations. The storage processor handles compression, caching, and movement. Longsys claims the process introduces no meaningful performance penalty. But that is one of the areas where independent testing will be important. Compression always requires work. The real question is whether the 5-nanometer engine can perform that work fast enough that the user barely notices. If the drive can compress at full interface speed, the savings could be substantial. If compression slows sustained writes or increases latency, the value becomes more complicated. Capacity is not useful if access becomes painfully slow. The 5nm chip at the center, the WM8500, is manufactured using a 5nm process. That does not automatically make it revolutionary. Process node names are not direct measurements, and a smaller node does not guarantee better architecture. But 5nm manufacturing provides a practical advantage. More processing logic can fit inside a compact controller while keeping power consumption manageable. Traditional SSD controllers already perform difficult tasks. They manage multiple NAND channels, calculate error correction codes, track wear, translate logical addresses, maintain caches, encrypt data, support PCI Express communication. Now add hardware compression, workload classification, predictive prefetching, and AI data scheduling. That requires more transistors, more processing, more memory, and careful power control. A storage controller cannot behave like a desktop CPU, consuming 100 watts. It lives inside a drive where heat can reduce performance and shorten flash memory life. The 5nm process gives Longsys room to add intelligence without turning the SSD into a small oven. The WM8500 also supports PCI Express 5.0, allowing high-speed communication with the host system. That bandwidth matters because the entire concept depends on moving model data quickly enough to hide the difference between SSD and DRAM. The drive does not need to become as fast as DRAM. It needs to become fast and predictable, enough that software can plan around it. The second trick, using SSD as slower memory. Compression creates the headline. HLC may create the bigger long-term impact. Longsys calls it high-level cache. The idea is to use the SSD as an extension of DRAM. Computers already use virtual memory. When physical RAM becomes full, the operating system moves some data to storage. Historically, this was painful. Hard drives were so slow that a computer using large amounts of virtual memory could become nearly unusable. Modern SSDs are much faster. They are still far slower than DRAM, but the gap can be managed more intelligently. Not all data needs immediate access. Some information is hot. The processor uses it constantly. Some is warm. It may be needed soon. Some is cold. It exists in memory but is rarely touched. HLC attempts to identify those categories. Hot data remains in DRAM. Warm and cold data moves to the SSD. If the system predicts correctly, the processor sees little delay because required data is fetched before it is needed. This resembles organizing a workshop. The tools used every minute remain on the table. Tools needed occasionally sit in a nearby drawer. Tools rarely used go into storage. A badly organized workshop forces the worker to walk across the building constantly. A well-organized one keeps the right objects close at the right time. Longsys says HLC can reduce required DRAM capacity by nearly 40% in a tested 256,000 token scenario involving a 122 billion parameter workload. That does not mean every computer can remove 40% of its RAM. It means this particular architecture reportedly achieved that reduction under a specific AI workload. The 397 billion parameter demonstration. The most eye-catching demonstration involved AMD hardware. Longsys says it jointly optimized an intelligent agent system built around the Ryzen AI Max Plus 395 processor. That AMD chip is designed for powerful local AI systems, combining CPU cores, graphics resources, and a large unified memory architecture. Using the SPU and ISA system, Longsys reports that the machine successfully deployed a 397 billion parameter model locally. That figure requires context. Deployed does not necessarily mean the model ran at cloud data center speed. It does not tell us the exact precision used for the weights. It does not reveal the token generation rate. It does not tell us how much of the model remained in memory and how much was streamed from storage, but it demonstrates the direction. A model too large to fit entirely inside conventional system memory can still run if inactive sections remain on the SSD and are loaded intelligently. Many modern models use a mixture of experts architecture. An MOE model may contain hundreds of billions of total parameters, but only a fraction activates for each token. Imagine a company employing hundreds of specialists. One question requires a lawyer, another requires an engineer, a third requires an accountant. The company does not need every employee in the meeting room simultaneously. The ISA system attempts to keep currently active experts in fast memory while storing inactive experts on the SPU-equipped SSD. When the system predicts that a different expert will be needed, it begins loading that expert early. If the prediction is accurate, the data arrives before the model asks for it. The delay becomes less visible. That is intelligent prefetching. The KV cache problem. Large language models face another memory burden, called the KV cache. As a model processes a conversation, it stores information about previous tokens, so it does not need to recalculate everything repeatedly. The longer the conversation, the larger the cache grows. A short prompt may be manageable. A document containing hundreds of thousands of tokens can consume enormous amounts of memory. Longsys says its system can move older or less active portions of the KV cache onto the SSD while keeping important sections in DRAM. Compression may reduce the space required further. Again, timing is everything. If the model suddenly needs an old section and the data has not been prefetched, inference can pause. The SSD becomes a bottleneck. If the scheduler correctly predicts future needs, the storage delay can overlap with computation. The model continues working while the next data block arrives. This is why the ISA software may matter as much as the WM8500 hardware. A fast drive with poor scheduling is still slow at the wrong moment. An intelligent scheduler can make slower storage feel faster by requesting data before the wait begins. Can this replace DRAM? No, at least not in performance-sensitive roles. DRAM operates with latency measured in tens of nanoseconds. NVMe SSD latency is usually measured in microseconds. A microsecond is 1,000 nanoseconds. That difference is enormous. Even a highly advanced SSD cannot become genuine system memory simply through clever software. It can, however, reduce the amount of expensive DRAM required. This distinction is important. The SPU does not replace the workbench. It makes the storage room more useful. The most frequently used tools remain on the workbench. The rest can move to an automated shelf that delivers them when requested. For AI systems, that can change economics. DRAM is expensive. High-capacity memory configurations increase device cost and power consumption. If a manufacturer can build a system with 96 gigabytes of DRAM that behaves like a larger memory machine under selected workloads, the savings could be meaningful. But the user experience depends on the workload. Interactive applications may be sensitive to small delays. Batch processing may tolerate them. Models with predictable expert activation may work well. Other architectures may not. One benchmark cannot answer every case. Could smart SSDs replace hard drives? Longsys also presents the SPU as a possible alternative to large-capacity hard drives. HDDs remain popular because they provide huge capacity at low cost. SSDs are faster, quieter, and more efficient, but large enterprise SSDs can be extremely expensive. Compression changes that calculation. If a 128 terabytes flash drive stores the same amount of suitable data as 256 terabytes of conventional capacity, its effective cost per stored terabyte falls. It may still cost more than hard drives, but total ownership includes more than purchase price. Hard drives use mechanical parts. They require more physical space. They consume energy. They produce vibration. They need cooling. They may fail differently. An SSD with intelligent compression could become attractive in environments where space, power, and access speed matter more than the lowest possible purchase price. However, flash endurance remains important. Compression may actually help by reducing the amount of data physically written to NAND. If 2 terabytes of original data compress to 1 terabyte, fewer flash cells need to be programmed. That could extend drive life. But only independent endurance testing can show how the complete system behaves under sustained heavy use. The SPU itself also creates new complexity. More intelligence means more firmware. More firmware means more opportunities for bugs. Storage errors are unforgiving. A graphics glitch is annoying. A corrupted database can be catastrophic. The questions Longsys still needs to answer. The company's claims are fascinating. They are not the same as a full independent review. We still need to know the sustained compression speed. Can the controller maintain performance when writing hundreds of gigabytes continuously? How does latency change when compression is active? What happens with data that compresses poorly? How much power does the SPU consume? How hot does the controller become? How consistent is the 2-to-1 ratio across real enterprise workloads? How does the system protect data if power fails during a compressed write? How many drives can operate together in a server? What is the cost compared with a conventional enterprise SSD? And perhaps most importantly, when can customers actually buy one at scale? A technology demonstration can show possibility. A commercial product must show reliability, support, firmware stability, and manufacturing volume. Storage buyers are conservative for a reason. They are trusting the drive with information that may be more valuable than the hardware itself. My take. My view is that the most important part of the WM8500 is not the headline capacity doubling. Compression is useful, but it depends heavily on the data. Some users may approach 2 to 1. Others may see far less. The deeper shift is architectural. Longsys is treating storage as a computing layer. For decades, the hierarchy was simple. The CPU computes. DRAM feeds the CPU. Storage waits. AI is breaking that arrangement because model sizes are growing faster than affordable memory capacity. The SPU offers another approach. Let the storage device perform part of the data work. Compress information before it consumes flash. Keep inactive model experts outside DRAM. Predict which data will be needed next. Move old KV cache entries into a lower-cost tier. None of those ideas individually eliminates the memory bottleneck. Together, they may make local AI systems far more capable. The risk is that intelligent storage becomes complicated storage. Prediction errors create delays, compression adds processing, firmware bugs create new failure modes, and company demonstrations may look better than mixed real-world workloads. Still, the direction makes sense. We are approaching a point where adding more raw storage and more raw DRAM cannot be the only solution. Efficiency must improve too. A 128 terabytes drive should not merely be a bigger bucket. It should understand how the bucket is being used. That is what the WM8500 is trying to become. Not just an SSD controller, a storage processor, a chip that turns capacity into something flexible, a chip that lets flash behave partly like memory, and under the right conditions, a chip that allows 128 physical terabytes to hold 256 terabytes of original data. The achievement is not that Longsys created storage from nothing. It is that the company may have found a better way to use what was already there. So what do you think? Would you trust a smart SSD that automatically compresses your files and manages part of your AI memory? Or would you prefer a simpler drive with predictable physical capacity and fewer layers of processing? Let me know your view in the comments. And if you want more grounded breakdowns of the chips, memory systems, and hidden hardware reshaping computing, subscribe to Eastern Engine, because the next storage revolution may not come from adding more flash. It may come from teaching the drive what to do with it. His name is Dong Hui. He is 39 years old. 6 years ago, a car accident left him paralyzed from the neck down. He couldn't move his fingers. He couldn't write. Something as ordinary as holding a pen had become completely impossible, and every specialist he'd seen told him the same thing in different words: this is permanent. Then surgeons placed a coin-sized chip between his skull and his brain. 11 months later, sitting in the courtyard of his home in China's Henan province, Dong Hui picked up a pen. Slowly, carefully, deliberately, he wrote his name. Then he wrote, "Thank you." Then he wrote the date. He later told journalists he was so overwhelmed that he missed a stroke in his own name. "I couldn't believe I was able to write again. I was so excited." That chip, the one that gave Dong Hui back his hands, just became the first invasive brain-computer interface in history to receive full commercial approval anywhere on Earth. Not a trial permit, not a research exemption, a product license. Available to real patients, covered by China's national health insurance. In production right now, scaling to meet demand. And here's the part that changes the entire story. While that was happening, Elon Musk's Neuralink, the most famous, most funded, most publicized brain chip project in the world, still has 21 people in an experimental trial. No commercial approval, no product license, no insurance coverage, anywhere. The race that everyone assumed Elon Musk would win, someone just crossed the finish line. And it wasn't him. To understand what just happened, you need to understand how this competition looked from the outside for the past several years. Neuralink was the story. Full stop. Elon Musk announced it, hyped it, described a future where paralyzed people would walk again, where blind people would see again, where the entire interface between human consciousness and computing would be reinvented. He is the most followed person on the planet. Every announcement got global coverage. Every trial update was front-page news. The assumption baked into almost every article written about brain-computer interfaces was simple. Neuralink leads, everyone else follows. Meanwhile, in Shanghai, a startup called Neurical Technology was quietly doing something different. No celebrity CEO. No viral announcements. No promises about controlling computers with your thoughts or uploading your memories. Just a research team, a partnership with Tsinghua University, one of China's most prestigious technical institutions, and a singular focus on getting one specific device approved for one specific group of patients. The device was called NEO. It's roughly the into commands for a robotic glove, allowing patients with severe hand paralysis to perform basic grasping movements they hadn't been able to do in years. In March 2026, China's National Medical Products Administration gave it full commercial clearance. 36 clinical trials, 32 of them completed in a compressed window in 2025 alone. And then, approved. Not for trials, for hospitals, for patients, for production. The first invasive brain implant ever cleared for sale anywhere in the world. Here's the counterintuitive part of this story. NEO is not the most powerful brain chip ever built. It almost certainly isn't. Neuralink's N1 chip penetrates the brain's outer cortex directly, accessing neural signals closer to their source and potentially enabling finer, more precise control. Neuralink's long-term ambitions, restoring sight, enabling full-body movement, eventually merging human consciousness with computing, are technically more audacious than anything NEO currently does. So how did the less aggressive device win the regulatory race? Because less aggressive and commercially viable are not opposites. They're often the same thing. NEO's design is epidural. It sits on top of the brain's protective membrane, rather than inside the brain tissue itself. A researcher at the University of Technology, Sydney, speaking to MIT Technology Review, explained why that distinction matters enormously in a regulatory context. An epidural approach carries significantly lower risk of bleeding and lower risk of signal loss over time than electrodes that penetrate the cortex. When a regulator is evaluating a device for broad commercial use, not just in a handful of carefully selected trial participants, but in real hospitals with real patients who have varying health conditions, risk profile is everything. NEO didn't win because it outperformed Neuralink. It won because it was designed to be approvable, not just impressive. And Neuralink had something else that Neuralink doesn't: state-level strategic backing with matching urgency. China has listed brain-computer interface technology as one of 6 national strategic priorities, alongside quantum computing and humanoid robotics. That designation isn't symbolic. It comes with coordinated funding, expedited regulatory pathways, and the kind of institutional alignment between researchers, companies, and government that compresses the timeline from lab to clinic in ways that are genuinely difficult to replicate in a system where commercial interests, regulatory bodies, and research institutions operate independently. Neuralink ran 32 of its 36 trials in a matter of months in 2025. That pace of clinical validation reflects a system operating in a different gear from what Neuralink has been navigating. The facts and the regulatory milestones are important, but there's a human being at the center of this story, and he deserves more than a footnote. Everything you do online is being watched: your provider, advertisers, even governments. NordVPN encrypts your connection, hides your location, and unlocks the open internet from anywhere. Grab the deal, link in the description. Dong Hui was paralyzed in 2018, 6 years of his life spent unable to use his hands. Then he saw something on television, a news report about another paralyzed man in China who had regained some movement through a brain-computer interface trial. He signed up for Neuralink's program in October 2023, 1 month after watching that report. The implant went in. The rehabilitation process began. Slowly, painstakingly, his brain learned to communicate with the device, and the device learned to interpret his brain. 11 months later, he wrote his name in his own courtyard. He also told journalists he hadn't expected it to work. He'd spent 6 years being told his condition was permanent. The moment he picked up that pen was the moment 6 years of that certainty collapsed. This is what NEO actually is, underneath all the regulatory language and competitive framing. It is a device that gave a man back the ability to write his own name, and it is now approved for use in a country of 1.4 billion people, covered by the National Health Insurance System, with more patients entering the program as production scales. The numbers behind that aren't just impressive, they're staggering. Hundreds of thousands of people in China live with the kind of spinal cord injury NEO is designed to treat. Here's the pattern that keeps appearing in technology, and it's directly relevant to everything covered on this channel. A technology is invented, usually in a Western lab, usually by researchers with enormous resources and high ambitions. For years, everyone watches that original team. They assume the leader stays the leader. They write articles about when the technology will mature, when it will become commercial, when it will change the world. All the attention stays focused on the most famous version of the thing, and then something else happens somewhere else. quietly, methodically, without the celebrity or the headlines. A different team, with different priorities, in a different system, makes different design choices. And while everyone is watching the famous version, the less famous version crosses a threshold that matters. It happened with glass chips. The semiconductor industry was fixated on transistors and lithography while the substrate layer changed underneath everyone. It happened with diamond cooling. NVIDIA's CEO was flying to China while most of the world was still debating whether diamond was even practical. And now it's happening with brain chips. Neuralink has more press coverage than every other BCI company combined. And a startup most people have never heard of, built in Shanghai with funding from Tsinghua University and backing from China's National Technology Strategy, just became the first to put a commercially approved brain implant into a patient outside a clinical trial. The pattern isn't that the famous version is wrong or that the quiet version is always better. The pattern is that fame and leadership aren't the same thing. And in technology, the milestone that actually counts isn't who announced it first, it's who shipped it first. NEO is the first. It will not be the only. China has at least 2 more BCI devices behind NEO in the pipeline. Neuroxess and StairMed are both developing competing implants domestically. The Beijing Brain Institute's BEINA01 system is expected to reach market by 2028. Within the span of roughly 2 years, China could have multiple commercially approved brain implants operating in its healthcare system, each generation learning from the one before it, while the rest of the world is still working through regulatory trials. The advantage this creates isn't just about one device, it's about data. Every patient who receives NEO generates real-world performance data in a commercial healthcare setting. That data, how the implant performs over months and years, which patient profiles respond best, which failure modes appear, and how often, is exactly the kind of evidence that makes second-generation devices better. And it is the kind of evidence that regulators in other countries will eventually require before approving anything. China now has a head start not just in commercial approval, but in the accumulation of long-term, real-world safety and performance data. That compounding lead is far harder to close than a regulatory gap. It's the same dynamic as the glass substrate story, the same dynamic as the diamond chip story. Being first doesn't just mean you got there early, it means every subsequent year of operation makes you harder to catch. For Neuralink specifically, the competitive picture has shifted in a way that doesn't get fully acknowledged. Neuralink's technical ambitions remain larger. Its long-term vision, the idea of a general-purpose brain-computer interface that goes far beyond motor rehabilitation, hasn't changed, but it is now competing in a landscape where a rival has commercial approvals, insurance coverage, real patients, and accumulating real-world data, while Neuralink is still adding participants to a clinical trial. That's a different kind of pressure than it was 12 months ago. Here's what strikes me most about this story, and it's something I keep coming back to. Neuralink had everything: the money, the attention, the most famous founder in technology, a decade of runway. And NEO, a startup from Shanghai with a fraction of the profile, shipped first. Not because Neuralink is more talented than Neuralink's engineers, both teams are world-class, but because Neuralink made a device that was designed to clear regulatory hurdles, rather than one designed to impress a keynote audience. They optimized for approval, not for ambition. And in the market for medical devices, approval is everything. The most powerful chip in the world is useless inside a lab. I think the Neuralink story is far from over. A device that actually penetrates the cortex and accesses finer neural signals will likely enable capabilities that NEO simply can't. But Neuralink now has to develop and prove those capabilities while a competitor is already in hospitals, already covered by insurance, already generating data, and already treating patients. That's a completely different race than the one Neuralink thought it was running. Here's my question for you, and I want your honest answer. Does this change how you think about Neuralink? Because here's the tension. NEO got to market first, but Neuralink's ambitions are larger. Is first to market in medicine the thing that matters most, or does the device with the higher ceiling eventually win regardless? Drop your actual opinion in the comments. This one I'm genuinely curious about. If you want to keep following these stories, the ones that rewrite which country leads in a technology that seems settled, subscribe to Eastern Engine and turn on notifications. Brain chips, diamond chips, glass chips, the substrate layer, the thermal layer, all of it connects. And all of it is moving faster than most people realize. Thanks for watching. See you in the next one. Jensen Huang flew to China. Not once, not twice, at least 3 times in 2026 alone. To Shanghai, to Beijing, to Shenzhen. And each time, industry insiders said the same thing. The CEO of the most powerful chip company on Earth wasn't there to sightsee. He was there because NVIDIA had a problem it couldn't solve at home. A problem so fundamental, so urgent, so deeply embedded in the physics of modern AI chips, that the man who runs a $3 trillion company had to cross the Pacific and walk into a Chinese lab to discuss it face to face. The problem is heat, and the solution, the one thing that can fix it, is the last material anyone expected: diamonds. Not as jewelry, not as decoration, as the beating heart of the next generation of AI chips. China controls more than 50% of global lab-grown diamond production. China holds the key patents. China's researchers published the breakthrough in Nature, and when Jensen Huang sat down in a meeting room with the CEO of a company called Henan Chaoying Diamond Technology, he wasn't browsing. He was there because NVIDIA's next-generation GPUs are already being redesigned around this material. By the end of this video, you'll understand the heat crisis that's quietly throttling artificial intelligence, why silicon can't solve it, why diamond is the answer physics has been sitting on for decades, and why China just positioned itself at the center of the most important material race in modern technology. Let's go. Here's something the AI industry doesn't put in its press releases. Every time a large AI model runs, every time it answers a question, generates an image, writes a line of code, the chips doing that work are fighting a war against heat. A war they are slowly starting to lose. Think about what's inside a modern AI data center. Row after row of server racks, each one packed with processors running at full throttle, around the clock. A single rack can now draw more than 1,000 watts of power. Most of it, somewhere between 30 and 35% of everything flowing into the building, gets consumed, not by the computation itself, but by the cooling systems trying to stop the hardware from melting. You are spending a third of your electricity bill just preventing your computers from destroying themselves. And it's getting worse, not incrementally worse, exponentially worse. Here's the physics that nobody can argue with. Every time chip designers increase transistor density, pack more processing power into the same piece of silicon, the heat generated per square millimeter goes up. There is no version of this math where that doesn't happen. You want more AI power, you need more transistors. More transistors means more heat. More heat means more cooling. More cooling means more power. More power means more heat. The loop closes and it tightens with every new generation of chips. Relevant studies show that for every 18 degrees Celsius rise in a chip's operating temperature, its failure rate increases by 2 to 3 times. That's not a marginal effect. That's a compounding disaster. You push the chip harder, it runs hotter, it fails faster, you spend more on replacements, and every dollar you save on computing gets swallowed by the thermal management problem you created in the process. Jensen Huang knows this intimately. At CES 2026, NVIDIA announced that its next-generation Vera Rubin architecture GPUs would adopt a completely new thermal solution, diamond copper composite cooling, combined with liquid cooling at 45 degrees Celsius. Not water chillers, not fans, diamond. The fact that the world's most advanced chip company just redesigned its flagship product around a material historically used in engagement rings should tell you something. Something big changed. Something broke through a wall that engineers have been staring at for decades. Silicon is remarkable, flexible, abundant, processable, scalable. The entire modern world is built on it. 60 years of Moore's Law didn't happen because silicon was convenient. It happened because silicon is genuinely extraordinary at being turned into transistors. Everything you do online is being watched. Your provider, advertisers, even governments. NordVPN encrypts your connection, hides your location, and unlocks the open internet from anywhere. Grab the deal, link in the description. But silicon has a dirty secret. As a thermal conductor, it's mediocre. Thermal conductivity is the measure of how efficiently a material moves heat away from a source. Silicon sits at about 150 watts per meter Kelvin. For comparison, copper, the metal used in most heat sinks and cooling pipes, sits around 400, 5 times better than silicon at moving heat. Diamond thermal conductivity sits at approximately 2,200 watts per meter Kelvin. That's 5 times better than copper, 14 times better than silicon. When engineers describe diamond as the ultimate semiconductor material, this is the number behind that claim. It's not marketing language, it's physics. Diamond moves heat the way a highway moves cars compared to a dirt road. But here's where the story gets interesting. The industry knew this. Scientists knew this for decades. Diamond's thermal properties have been documented for generations. So why wasn't it already in every chip, in every server rack, in every data center on Earth? Because until very recently, you couldn't make it. Not at scale, not at the quality a semiconductor requires, not at a price that made any commercial sense. That wall just came down. In December 2024, researchers from 3 Chinese institutions, Peking University, the Southern University of Science and Technology, and the University of Hong Kong, published a paper in Nature. The subject was the economical production of ultra-thin smooth diamond films at industrial scale. Read that again. Not diamond synthesis in a lab, not a proof of concept, economical, industrial scale. This was the manufacturing breakthrough that the semiconductor industry had been waiting for without fully admitting it was waiting for it. The method for producing lab-grown diamonds through chemical vapor deposition had existed for years, but it was slow, expensive, and produced material with impurities and surface roughness that semiconductor applications simply couldn't tolerate. Getting a diamond film smooth enough to bond to a chip is a different problem from growing a diamond. A chip's contact surface needs to be flat to tolerances measured in fractions of a nanometer. Rough diamond is useless for this application no matter how good its thermal properties are. The Peking University paper cracked that. And when it landed, the chip industry did not respond quietly. NVIDIA's supply chain team began validation work almost immediately. A Chinese diamond company called Chaoying Diamond confirmed that its diamond copper composite material had passed NVIDIA's supply chain validation for use in high-power density AI chip thermal management. Jensen Huang went to China, met with Henan Chaoying Diamond Technology, and discussed industrialization. This is not a rumor, this is not speculation. The CEO of NVIDIA met with a Chinese diamond chip company because the physics demanded it. Let's be precise here, because this is the part where people misunderstand the technology. And misunderstanding it leads to comments that miss the point. Diamond is not replacing silicon as the material transistors are made from. Not yet. Silicon is still where the transistors live. What diamond is doing is solving the thermal layer, the path that heat takes after it's generated and before it destroys the chip. In the current architecture, heat generated by transistors has to travel through several material layers before reaching the cooling system. Each layer acts as a speed bump. The worse each material's thermal conductivity, the longer heat lingers near the transistors, and the hotter they run. Diamond replaces the worst of those layers. Inserted as a substrate or a heat-spreading layer between the chip and the cooling system, it essentially builds a superhighway for heat to escape. The chip runs cooler. Cooler chips run faster. Faster chips are more efficient. More efficient chips use less cooling. Less cooling means less power. Less power means lower cost. Huawei's engineering team, working with Xiamen University, has already demonstrated the practical results of this in a real system. Using diamond heat dissipation technology integrated with glass interposer chip packaging, they reduced the maximum junction temperature by 24.1 degrees Celsius and cut the chip package's thermal resistance by 28.5%. That's not a marginal improvement. In chip thermal engineering, cutting junction temperature by more than 24 degrees is the difference between running at the edge of safe limits and running with comfortable headroom to push performance higher. Apply that same math to a data center with thousands of chips. Multiply the efficiency gain across millions of server hours. The numbers stop being impressive and start being civilization scale. Here's where the strategic picture snaps into focus, and it's genuinely surprising in a way that the glass substrate story was. China produces more than 50% of the world's lab-grown diamonds, not by a narrow margin, by dominance. The province of Henan is the global epicenter of synthetic diamond production, home to companies like Huanhe Whirlwind, Liliang Diamond, and North Industries Red Arrow. These companies have spent years perfecting the high-temperature, high-pressure, and chemical vapor deposition processes used to grow gem-quality diamonds at scale. That industrial muscle, the accumulated process knowledge, the equipment, the yield management, transfers directly to semiconductor-grade diamond production. It's the BOE story all over again. In the glass substrate videos, we talked about how China's display glass manufacturing infrastructure gave it an unexpected edge in semiconductor glass. The same pattern plays out here, except diamond production is even more concentrated. More than half the world's synthetic diamond capacity sits in Chinese factories that were optimized for jewelry but are now pivoting to chips. And those factories are not starting from scratch on the semiconductor application. The Nature paper gave the industry the roadmap for ultra-smooth, ultra-pure diamond films. Chinese companies are now certifying against NVIDIA's supply chain requirements. Huawei has filed patents combining diamond thermal management with glass substrate packaging, creating a hybrid architecture that is genuinely novel, using two of the most advanced packaging materials simultaneously in a single chip system. Meanwhile, China's diamond stocks on the A-share market surged more than 90% year to date. Not because of jewelry demand, because sophisticated investors read the same supply chain signals NVIDIA sent when it redesigned its next-generation GPU around diamond cooling. The market was paying attention. Most of the world's tech press wasn't. Step back, take a breath. Think about what the pattern looks like from altitude. Glass substrate, a material for packaging AI chips that outperforms plastic by a factor of 10. China positioned itself at the manufacturing frontier before most of the industry was paying attention. We covered that. 2 videos, a combined 100,000 views, and the story isn't finished. Diamond, a material for managing AI chip heat that outperforms everything else in existence by a factor of 5. China controls more than half the world's production capacity, holds the key industrial patents, and just cracked the manufacturing problem in a Nature paper. Jensen Huang flew across the Pacific to meet with a Chinese diamond company to discuss it. These are not isolated stories. They are chapters in the same book, and the book is about the layer of the semiconductor industry that nobody was guarding, the packaging and thermal management stack that sits between the raw silicon and the cooling system, the layer that determines whether the most powerful chips in the world run at their potential or throttle themselves to avoid melting. Transistors get all the headlines. This layer is increasingly where AI's actual limits are set. And China, quietly, methodically, and in some cases using manufacturing expertise built for completely unrelated industries, is building a dominant position across it. Glass first, diamond second. The question is, what comes third? Here's my honest view, and I'll make it direct. I've covered glass chips, I've covered the NVIDIA story, I've covered the Huawei Tau scaling law. But this diamond story is the one that genuinely surprised me. Not because the technology is unexpected, but because the convergence is. That kind of accidental advantage is harder to dislodge than a planned one, because it wasn't built to be a competitive weapon. It just became one. And NVIDIA's response, redesigning its flagship GPU around diamond cooling, and sending its CEO to meet with Chinese suppliers to figure out how to get it at scale, is the clearest possible signal about how seriously the world's most advanced chip company takes this material. The AI heat crisis isn't going away. Physics doesn't negotiate. And the country that controls the thermal management stack is going to have a seat at the table every time an AI chip is designed, for the next decade at minimum. That, to me, is the real story here. Here is the question I want you to think about honestly. We are watching China build an advantage in the materials layer of AI chips. First glass, now diamond. Not through copying, but through manufacturing expertise built for completely different industries. Is that a more dangerous kind of lead to compete against than a straightforward technology gap? Or do you think the West's chip designers will just engineer around the thermal problem entirely and make the material irrelevant? Drop your actual opinion in the comments. I genuinely want to know which way people are leaning on this one. If this kind of deep dive, the material, the supply chain, the strategic layer most coverage misses completely, is why you come here, subscribe to Eastern Engine and turn on notifications. We cover the breakthroughs that matter before they become obvious. Glass chips, diamond chips, whatever comes next in this stack, you'll see it here first. Thanks for watching. I'll see you in the next one. For years, the world's fastest supercomputers have followed one dominant formula. Start with powerful central processors. Add enormous numbers of specialized GPU accelerators. Connect everything with an ultra-fast network. Then, use those GPUs to perform the mathematical work that would overwhelm ordinary CPUs. America's El Capitan follows that model. It combines AMD server processors with AMD Instinct MI300A accelerators and delivers more than 1 quintillion calculations every second. It held the official title of the world's fastest publicly ranked supercomputer. Until now, a previously unlisted Chinese machine called Lineshine has entered the official TOP 500 ranking at number 1. Its verified performance is 2.198 exaflops. America's El Capitan recorded 1.809 exaflops. That places the Chinese system approximately 21.5% ahead on the benchmark used to determine the global ranking. But the most surprising part is not simply that China moved into first place. It is how Lineshine got there. The machine reached more than 2 exaflops of sustained double-precision computing without dedicated GPU accelerators. No NVIDIA GPUs. No AMD Instinct accelerators. No Intel data center GPUs. Instead, Lineshine uses millions of custom Chinese CPU cores, a proprietary interconnection network, and a domestic software stack. It is the first publicly ranked supercomputer to sustain more than 2 exaflops using CPUs alone. That does not automatically make it the best AI computer in the world. It does not mean GPUs are suddenly obsolete, and one benchmark can never describe every workload a machine may encounter. But this result is official. China has taken the #1 position on the TOP 500 for the first time since 2017, and it did so by rejecting the architecture used by almost every other leading exascale machine. What officially #1 actually means. The top 500 list has ranked the world's most powerful publicly disclosed supercomputers since 1993. It is updated twice each year. To determine the ranking, systems run a benchmark known as High Performance LinPack, or HPL. HPL asks the computer to solve an enormous system of dense linear equations using high-precision 64-bit floating-point mathematics. This kind of calculation appears in scientific simulation, engineering, and numerical analysis. The benchmark measures how many floating-point operations the machine can sustain each second while solving the problem. A petaflop is 1 quadrillion operations per second. An exaflop is 1 quintillion. Lineshine sustained 2.198 exaflops. Written out, that is roughly 2.198 quintillion floating-point operations every second during the benchmark. The number is not a theoretical marketing figure. Lineshine's theoretical peak is higher, at approximately 2.736 exaflops. But theoretical peak assumes every component operates perfectly. Every cycle is fully utilized and no time is lost to communication, memory access, or software overhead. Real machines never maintain theoretical peak continuously. Lineshine converted slightly more than 80% of its theoretical capability into measured HPL performance. That is one of the most important details in this story. Building millions of processor cores is difficult. Keeping them busy at the same time is much harder. A supercomputer does not become fast merely because it contains many processors. The processors must communicate, share data, synchronize, and divide a single enormous problem without spending most of their time waiting. Lineshine's 80% result suggests that its architecture is not simply large, it is highly coordinated, inside the CPU-only machine. Lineshine is installed at the National Supercomputing Center in Shenzhen. The machine was built by the Shenzhen Cloud Computing Center and is based on a custom platform called Lingkun. At its core is a Chinese processor known as the LX2. Each LX2 contains 304 CPU cores running at 1.55 GHz. The complete system contains 13,789,440 cores. Divide that total by 304, and the architecture appears to use roughly 45,360 of these processors. That is not 45,000 individual desktop computers. These processors are installed in densely packed computing nodes, surrounded by memory, cooling equipment, power distribution systems, and the network required to connect the entire machine. A modern GPU may contain thousands of smaller parallel computing units. Lineshine instead spreads its work across a vast population of general-purpose CPU cores. The individual clock frequency of 1.55 GHz may sound modest compared with a consumer desktop processor that can exceed 5 GHz. But supercomputers are not built to make one core run as fast as possible. They are designed to make millions of cores work together. A higher clock frequency increases power consumption and heat. At this scale, efficiency, parallelism, and communication matter more than winning a single core benchmark. Imagine trying to move a mountain. One extremely strong worker cannot do it. 45,000 organized teams might, but only if every team knows exactly which section to move, where to place it, and when to act. Without coordination, adding more workers can make the project slower. That is why the processor count is only half the story. The hidden weapon is the network. Every processor inside a supercomputer needs data. A calculation performed on one node may depend on a result produced somewhere else. If those results move slowly, the processors sit idle. At exascale, even tiny communication delays become enormous when repeated trillions of times. Lineshine connects its processors using a proprietary Chinese interconnect called Lingqi. The public technical information remains limited, but the benchmark results reveal that this network is doing serious work. HPL involves regular, predictable mathematics, making it easier to divide efficiently than many real scientific applications. However, Lineshine also ranked first on a second benchmark called HPCG. HPCG stands for High Performance Conjugate Gradients. Unlike HPL, it places greater pressure on memory access, communication, and irregular data movement. These are the parts of supercomputing that often prevent theoretical performance from becoming useful performance. Lineshine achieved approximately 22 petaflops on HPCG. El Capitan achieved around 17.4 petaflops. That places Lineshine roughly 26% ahead on this second measurement. This result is important because it weakens the simplest criticism. The machine did not merely win one highly optimized matrix calculation while collapsing on a more communication-intensive workload. It also led the benchmark intended to represent patterns found in real scientific applications more closely. HPCG is still only a benchmark. No single test can reproduce climate modeling, fluid dynamics, molecular simulation, seismic analysis, and every other scientific workload. But finishing first on both HPL and HPCG suggests that Lineshine's interconnect and memory system are not afterthoughts. The architecture appears balanced enough to keep millions of CPU cores supplied with data. Why build a supercomputer without GPUs? The obvious question is why anyone would avoid accelerators. GPUs became dominant in supercomputing for a reason. A CPU is designed to handle a broad range of instructions. It is flexible. It can manage operating systems, complicated decision-making, serial code, and workloads with unpredictable branches. A GPU is narrower but massively parallel. It excels when the same mathematical operation must be applied across enormous arrays of data. Scientific simulations and neural networks are filled with those operations. That is why America's leading machines use accelerators. El Capitan combines AMD EPYC processors with MI300A accelerated processing units. Frontier uses AMD MI250X accelerators. Aurora uses Intel GPU Max accelerators. Europe's Jupiter Booster uses NVIDIA Grace Hopper superchips. Against that field, Lineshine looks almost deliberately unconventional. One possible advantage is programming simplicity. Accelerated systems divide applications between CPUs and GPUs. Developers must decide which code runs where, move data between different memory spaces, and optimize software for specialized hardware. A CPU-heavy machine can provide a more uniform programming environment. The same processor type handles more of the workload. That does not make programming easy, especially across nearly 14 million cores, but it can reduce the architectural divide between a host processor and an accelerator. CPU-based systems may also perform well on workloads that contain complex control logic, irregular memory access, or sections that do not map cleanly onto GPUs. The disadvantage is efficiency. GPUs can perform far more parallel arithmetic per watt on suitable workloads. To compete without them, Lineshine must deploy an enormous number of CPU cores and keep those cores highly utilized. The machine is not proving that accelerators were a mistake. It is proving that accelerator-free exascale computing remains possible when processors, memory, software, and networking are designed as one system. An entirely custom computing stack. Lineshine is not only unusual because it avoids GPUs, its major layers are Chinese developed. The processors are custom LX2 chips. The computing platform is called Ling Kun. The interconnect is Ling Qi. The operating system is Qilin. The benchmark submission also lists a customized compiler and locally adapted mathematical software. This matters because supercomputer performance depends on more than silicon. A powerful processor running poorly optimized code can waste most of its theoretical capability. The compiler must translate software into instructions that exploit the processor's architecture. The mathematical libraries must perform common operations efficiently. The operating system must coordinate resources across thousands of nodes. The communication software must move messages across the network without creating unnecessary delays. When a system achieves 80% of its theoretical peak on HPL, that usually means multiple layers have been optimized together. The hardware team cannot work in isolation. Neither can the software team. The machine behaves less like a collection of separate products and more like one enormous engineered instrument. This full-stack approach may be the real achievement. China did not simply build a processor and insert it into an existing American or European supercomputer design. It submitted a complete domestic platform capable of taking first place on two major rankings. The power bill behind the performance. There is a cost. Lineshine draws approximately 42.2 megawatts while delivering its submitted performance. That is industrial-scale power consumption. At that rate, operating continuously for 24 hours would require more than 1,000 megawatt-hours of electricity. Cooling the hardware adds another major engineering challenge. Every watt entering a processor eventually becomes heat. Thousands of high-density computing nodes must be cooled continuously, because overheating can reduce performance or damage components. Lineshine achieves an energy efficiency of approximately 52.07 gigaflops per watt. El Capitan records around 60.94 gigaflops per watt. That makes the American system roughly 17% more efficient on the reported metric. This is where the accelerator advantage becomes visible. Lineshine wins the raw HPL ranking. El Capitan produces more computation from each watt. Neither result cancels the other. The Chinese system was designed to maximize sustained high-precision CPU performance. The American system combines CPUs and specialized accelerators to improve performance across traditional simulation and mixed precision workloads. Two different architectural philosophies produce different strengths. In an era when electricity and cooling are becoming limits on both supercomputers and AI data centers, energy efficiency cannot be ignored. Winning the performance crown is impressive. Operating the machine economically for years is a separate challenge. The AI benchmark changes the story. This is the most important caveat. Lineshine is officially number 1 on HPL. It is also number 1 on HPCG. But when the benchmark shifts toward lower precision mathematics used heavily in artificial intelligence, the ranking changes. The HPL MXP benchmark measures mixed precision performance. Traditional scientific calculations often use 64-bit precision because tiny errors can accumulate and affect the final result. Many AI workloads can use 32-bit, 16-bit, 8-bit, or even lower precision numbers. Specialized accelerators are extremely fast at these operations. On HPL MXP, Lineshine achieved approximately 7.92 exaflops and ranked 4th. El Capitan achieved 16.7 exaflops and remained number 1. That means El Capitan delivered more than twice Lineshine's mixed precision result. This is why the phrase "world's fastest supercomputer" needs context. Lineshine is the fastest system on the official benchmark used to rank the top 500. That benchmark measures sustained double precision performance. It does not prove that Lineshine will train the largest AI model faster than El Capitan. It does not prove that it will outperform GPU systems on every application. For AI-style low-precision mathematics, El Capitan's accelerators provide a major advantage. The two machines are like different vehicles. Lineshine is an enormous high-precision freight engine capable of moving a massive scientific workload. El Capitan is a hybrid machine with specialized engines for different terrain. On the official straight-line test, Lineshine wins. On the mixed precision AI test, El Capitan pulls far ahead. Does no GPU mean the return of the CPU? Not exactly. GPUs are not disappearing from supercomputing. In fact, accelerator adoption continues to grow across the TOP 500. AI demand is making specialized low-precision computing more important, not less. Lineshine demonstrates a different point. There is no single correct architecture for every supercomputer. The best design depends on the workload. If a research center prioritizes high-precision scientific simulation, CPU flexibility, and a uniform programming environment, a massive CPU-based design may remain competitive. If the goal is training neural networks or running mixed precision mathematics, specialized accelerators are difficult to beat. Future systems may become even more heterogeneous. They may combine CPUs, GPUs, AI accelerators, photonic processors, and custom chips, assigning each task to the hardware that performs it most efficiently. Lineshine stands out because it moves in the opposite direction. Instead of adding more types of processors, it scales one processor architecture to an extraordinary level. That simplicity at the component level creates extreme complexity at the system level. Nearly 14 million cores must operate as one computer. The fact that they do so efficiently enough to reach 2.198 exaflops is the central engineering story. What will China use it for? The public top 500 entry identifies Lineshine as a research system at the National Supercomputing Center in Shenzhen. Supercomputers at this level can support many categories of scientific work. Possible workloads include weather forecasting, materials discovery, fluid dynamics, engineering simulation, molecular modeling, and large-scale numerical research. However, the precise workload mix and access policies for Lineshine have not been fully disclosed publicly. That lack of detail matters. Benchmark numbers tell us what the machine achieved during controlled tests. They do not tell us how much useful scientific work it completes each week, how easy it is to program, or how reliably it operates under sustained demand. A supercomputer becomes valuable when researchers can use it efficiently. Applications must be rewritten or optimized for the architecture. Scientific teams need access. Storage systems must feed enormous datasets into the machine. The system must remain stable, while millions of components operate simultaneously. China has demonstrated the hardware platform. The next evidence will come from published scientific results produced using it. Why this changes the global supercomputing picture. Before Lineshine entered the ranking, the top positions were dominated by American accelerated systems. El Capitan was first, Frontier was second, Aurora was third. The United States had established a clear lead in publicly ranked exascale computing. Lineshine did not slowly climb from 10th place to 5th and eventually first. It appeared directly at the top. That creates two important changes. First, the official performance lead has moved back to China for the first time since 2017. Second, the machine expands the definition of what an exascale system can look like. The industry had been moving toward the belief that accelerators were practically mandatory at this scale. Lineshine proves that a CPU-only approach can still win the traditional performance crown. Whether that approach becomes widely copied is another question. The power demand is substantial. Its AI performance is weaker than El Capitan's, and the public technical details are not yet deep enough for outside experts to evaluate every design decision. But the result cannot simply be dismissed. Top 500 accepted the submission. The measured numbers place Lineshine first, and its HPCG result strengthens the claim that this is more than a narrowly optimized demonstration. The honest catch. There are four major caveats. First, Lineshine is number one on specific benchmarks, not automatically on every real application. Second, its lack of dedicated, low-precision accelerators limits its advantage in modern AI computing. Third, it consumes more power per unit of reported performance than El Capitan. Fourth, many architectural details remain proprietary or publicly unexplained. We know the processor core count, clock frequency, system platform, interconnect, operating system, and benchmark results. We know much less about the internal design of the LX2 core, its memory hierarchy, vector capabilities, manufacturing process, packaging, and the exact topology of the Lingqi network. Those details would help explain how China reached this level without GPUs. Until more information or scientific performance results appear, some questions must remain open. But uncertainty around the details does not erase the verified result. Lineshine sustained more than 2 exaflops of high-precision performance and displaced El Capitan from the top of the official list. My take is that the number one ranking is important, but the architectural divergence is even more important. China did not win by building a slightly larger copy of El Capitan. It chose a different route. America concentrated enormous parallel performance inside advanced accelerators. China distributed the work across nearly 14 million custom CPU cores and built a network powerful enough to keep them synchronized. The American design is more efficient and much stronger on mixed precision AI mathematics. The Chinese design is now faster on the traditional HPL benchmark and also leads HPCG. This is not a simple story of one country possessing better technology in every category. It is a story of two systems optimized around different strengths. Lineshine shows what can happen when processor design, networking, software, and system architecture are developed together around one objective. It also shows that mature technologies can still produce surprising results. The CPU was supposed to become a supporting actor in the exascale era. Lineshine put millions of CPUs at the center of the machine and reached number one. The question now is whether this is a one-time engineering achievement or the beginning of a broader CPU-first supercomputing strategy. Will China continue scaling the Lincoln platform? Will future LX processors improve energy efficiency and mixed precision performance? Will Lineshine produce scientific results that justify its enormous size and power demand? And will American laboratories respond with even larger accelerated systems? The supercomputer race has not ended. It has become more interesting because the leading machines are no longer following the same blueprint. So what matters more to you? Should Lineshine be considered the world's most powerful supercomputer because it officially ranks first on HPL and HPCG? Or does El Capitan's stronger efficiency and AI-oriented performance make it the more capable overall machine? Let me know your view in the comments. And subscribe to Eastern Engine for more grounded coverage of the chips, materials, and computing systems changing the global technology industry. Because China did not take the supercomputer crown by copying the dominant design. It took the crown by proving there was another road to exascale. China just spent over $1 billion on glass. You read that right. Not on transistors, not on the giant machines that print them, on glass. And that single, strange-sounding bet may have just exposed the one weakness sitting underneath every advanced chip on the planet. A weakness almost nobody outside the industry is talking about. Here's what makes this the most fascinating story in technology right now. It isn't really about what China built. It's about what China understood that the rest of the industry quietly overlooked. While everyone else was fighting over one part of the chip, China looked at a completely different part, the part holding the whole thing together, and realized that's where the real bottleneck was about to appear. By the end of this video, you'll understand exactly what that weakness is, why it's getting worse at the worst possible moment, why glass is the unlikely answer, and why a single billion-dollar bet could reshape who controls the next decade of computing. Let's get into it. For the last several years, the global conversation about chips has revolved around one thing: making transistors smaller. Who can shrink them further? Who can pack more of them onto a piece of silicon? The entire industry, and a huge amount of government policy, has been organized around that single race. At the center of that race is a machine made by a Dutch company called ASML. Its extreme ultraviolet lithography systems are the only tools on Earth capable of printing the most advanced transistors onto silicon. Each machine weighs about as much as 2 fully loaded school buses. Each one costs close to $200 million. Only a tiny handful of suppliers worldwide can build even a single component inside one. These machines are, without exaggeration, among the most complex objects humanity has ever manufactured. So the logic that took hold across much of the industry was simple: control the machine, control the chips. Whoever can't access the most advanced lithography can't make the most advanced transistors, and therefore can't lead in AI. It's a clean argument, and it has one enormous blind spot. It only holds if shrinking transistors is the only path to more powerful computing. China, quietly and very deliberately, decided that it isn't. Think of it like a race where one competitor has locked up the world's only supply of racing tires. Most teams would spend years trying to reverse engineer that tire. China looked at the track instead and built a completely different vehicle, designed for a surface those tires were never made for. That surface is called advanced packaging, and the vehicle is glass. Here's the part most people don't realize. The most powerful AI processors being built today aren't really single chips anymore. They're clusters, dozens of smaller chips, called chiplets, wired together on a shared platform and designed to behave as one unified processor. That shared platform is called the substrate. It's the foundation everything sits on. It connects the chiplets to one another, carries the electrical signals between them, and helps manage the enormous heat they produce. If the chiplets are buildings, the substrate is the ground they're built on. And right now, that ground is made of organic material, essentially a very sophisticated, highly engineered form of plastic. This is the key reframing of the entire story. China isn't trying to outshrink anyone's transistors. China is trying to replace the floor that everyone else's chips are standing on. While the rest of the industry was guarding one door, China simply walked around the building. To understand why that's such a powerful move, you have to understand what's happening to those plastic foundations right now, and why they're starting to fail at the worst possible moment in the history of computing. Here's something the chip industry doesn't put in its marketing. The most powerful AI processors ever made are being held together by what is, at its core, a very advanced form of plastic. Not as a metaphor, literally. The substrate is built from organic resins and fiberglass weaves, materials that have served the industry faithfully for decades. Materials designed for a world where chips were smaller, cooler, and far simpler than what's being built today. That world is gone. The AI chips driving the current boom are enormous. A single advanced AI processor package today can stretch beyond 8,000 square millimeters. To picture that, lay 4 standard playing cards side by side. That's roughly the surface area. And across that entire surface sit billions of microscopic connections, all communicating at once, all generating heat, and all depending on one thing: the substrate beneath them staying perfectly, dimensionally still. Here's the brutal catch. It doesn't stay still. Organic substrates expand and contract with temperature. Every time a chip powers up, heats, and cools back down, the foundation moves. Not visibly, not dramatically. We're talking shifts measured in parts per million. But at the scale of a modern AI package, parts per million isn't a rounding error. It's a slow-motion disaster. Those microscopic connections, some of them finer than a strand of human hair, begin to drift. Slowly at first, then faster, until the clean electrical path between two chiplets becomes inconsistent, then degraded, then broken entirely. Think of a long suspension bridge in a heat wave. The cables don't snap, they just stretch slightly. But if every measurement in the original design assumed they'd never move, that slight stretch is enough to throw the whole structure out of tolerance. That's what's happening inside the most advanced AI chips on Earth right now. Not a dramatic explosion, a slow, invisible drift that engineers can measure but struggle to stop, because the material causing it is baked into 50 years of production lines, supply chains, and manufacturing processes. And here's the detail that puts it all in perspective. This problem was perfectly manageable when chips were small and AI workloads were modest. But the entire trajectory of AI hardware points in one direction: larger packages, denser connections, higher power, more heat. Every single variable that makes organic substrates struggle is getting worse at the same time. So the question was never whether plastic substrates would hit their limit. The question was who would have the replacement ready when they did. That replacement has a name, and what it can do sounds almost impossible. You've probably held the answer in your hand. Not in a chip lab, not in a data center, in your kitchen. A borosilicate glass dish, the kind you bake with, survives dramatic temperature swings without cracking or warping. You pull it from a hot oven, set it on a cool countertop, and it holds its shape. That stability isn't luck. It's a fundamental property of the material. Now scale that principle down to something thinner than a fingernail. Engineer it to tolerances that can only be verified under specialized lab equipment, and you start to understand what semiconductor-grade glass substrates really are. This isn't window glass. It isn't the glass on your phone screen. It's a purpose-built material designed to solve exactly the problems organic substrates can't. Start with stability. Where plastic expands and contracts with every heat cycle, glass holds its dimensional shape with the rigidity of steel. The connections printed onto its surface stay where they were placed, through power-up, through full load, through cool-down, with no drift, no degradation, no invisible creep pulling chiplets out of alignment. Then there's connection density. Today's best organic substrates can only pack so many electrical connections into a given area before signal interference and manufacturing limits make tighter spacing impossible. Glass can support up to 10 times that density. 10 times. And here's what makes it genuinely remarkable. Signal quality improves at the same time. Organic materials absorb and scatter electrical signals as they travel. Glass doesn't. A signal that enters one side arrives at the other, cleaner, faster, and with less interference, which means chiplets can communicate more reliably without the system constantly compensating for a degraded signal. But the real unlock isn't any single property. It's what they make possible together. Once you have a foundation that doesn't warp, that carries 10 times the connections, and that keeps signals clean across large distances, you can build chiplet packages that plastic could never support. Packages stretching far beyond today's limits, where designers stop worrying about the foundation failing and start designing for the limits of physics itself. That's the prize. Not a better chip, a better foundation that makes every chip better. So if glass is this good, the obvious question is, why hasn't everyone switched already? Picture a drinking straw. Now shrink it until it's thinner than a single strand of human hair. Now imagine drilling thousands of those, perfectly vertical, perfectly parallel, perfectly spaced, through a sheet of glass the thickness of a fingernail, without cracking it and without introducing a single invisible fracture that might only reveal itself months later under operating stress. Now imagine doing that millions of times a day, at a success rate high enough to actually make money. That's the through-glass via problem, and it's the reason glass substrates have been understood in theory for years while remaining out of reach in practice. A via is just a vertical electrical connection, a channel drilled through the substrate so signals can travel between layers. In plastic, vias are punched or laser drilled through forgiving, flexible material. Glass is neither forgiving nor flexible. It's rigid and brittle, and it punishes imprecision with fractures that spread invisibly through the material until the whole substrate fails. Sometimes during manufacturing, sometimes during testing, and sometimes, devastatingly, after the finished chip has already shipped. And drilling is only the first hurdle. Those holes then have to be filled with conductive metal, usually copper, bonded to the glass without creating stress at the interface. Glass and copper expand at different rates under heat. If that interface isn't engineered perfectly, thermal cycling creates microscopic separation between the copper and the glass wall. The via still looks intact. The signal path still measures clean, right up until it doesn't. Then there's the issue engineers don't love discussing publicly: yield. The percentage of substrates that survive the full process without a defect. Early pilot lines produced yields so low that the cost per usable substrate made commercial production impossible. You can't build a global supply chain on a material that fails more often than it succeeds. On top of that, there's flatness. A glass substrate has to stay flat to tolerances measured in single-digit micrometers across its entire surface, and 1 micrometer is roughly 1/70th the width of a human hair. Holding that flatness through the heat, chemicals, and physical handling of a full production line took years of dedicated engineering just to approach. And even after a company solves drilling, filling, yield, and flatness, it still has to qualify the whole process with semiconductor customers, a validation step that can take 2 to 3 years. during which the line earns almost nothing, while the capital sits committed. That combination, brutal process complexity, punishing yields, multi-year qualification, and enormous upfront cost, is exactly why most of the industry treated glass substrates as a long-term research project rather than an urgent priority. China looked at those same barriers and saw something completely different, a moat it could cross before anyone else even arrived at the water's edge. Here's what most people get wrong about China's position. They assume China is starting from scratch, throwing money at a brand new technology and hoping state funding alone can compress decades of learning into a few years. That's not what's happening. China isn't starting from scratch. It's redirecting. There's a company called BOE. Outside the display industry, most people have never heard of it. Inside it, BOE is impossible to ignore. It's one of the largest manufacturers of display glass on Earth, the panels inside televisions, monitors, tablets, and smartphones. Its facilities are so vast that a single BOE campus can cover more floor space than many international airports. And to make display glass at that scale, BOE spent years building exactly the kind of precision, large-format glass handling infrastructure that semiconductor substrate production requires. Think about what that means. Precision glass cutting at massive scale, flatness control across large surfaces, high-volume process lines where tolerances are measured in micrometers and yield is tracked obsessively, because a failed panel at the end of a line is a direct hit to profit. The equipment categories are different, the end product is different, but the manufacturing discipline, the process philosophy, and the capital infrastructure are directly transferable. And this is the part that reframes everything. The glass substrate challenge isn't primarily a material science problem anymore. The physics are understood, the engineering principles are established. The real problem is manufacturing, handling precision glass at high volume with the process control and yield management that commercial production demands. And that's the exact category of problem BOE has been solving at scale for years. Not for chips, for screens. But the muscle memory is the same. BOE isn't alone either. Several other Chinese firms have been attacking the through glass via problem directly. The drilling, the filling, the bonding, the yield, with serious capital and real urgency. That only makes sense if the goal isn't a research paper, but production volume. And much of this has been backed by China's national semiconductor investment funds, the same coordinated state machinery that has a track record of turning strategic priorities into industrial reality, however long it takes. Numbers can feel abstract until you give them a shape. So here's the shape of this one. Since 2023, China's national semiconductor funds, combined with direct corporate investment, have directed over $1 billion specifically into glass substrate technology, not into basic research, into production-oriented engineering, yield improvement, process qualification, through glass via scaling, and the supply chain infrastructure needed for commercial volume. And here's what that number tells you, that the figure alone doesn't. Investment at that scale, aimed at that specific problem, with that level of coordination, doesn't happen because someone found an interesting paper at a conference. It happens because a strategic decision was made. A decision that this technology will define the next generation of chip packaging, and that China intends to lead it. That decision appears to have been made around 2022, at roughly the same moment much of the rest of the industry was confident it had the chip race locked up through lithography. And $1 billion isn't the ceiling. It's the foundation. A single glass substrate production line can cost between $500 million and $1 billion to build and qualify. So the money already deployed was enough to seed the process learning. Reaching full volume will require multiples of that, and in China's model, once the strategic value is proven, the capital follows. Here's why this is the most time-sensitive part of the whole story. Semiconductor manufacturing rewards the first mover in a way that compounds and becomes almost impossible for latecomers to undo. It's not just about owning the equipment, it's about the process knowledge that accumulates on a real production line over months and years of running real material through real tools and solving real problems. That knowledge doesn't transfer through patents or papers. It lives in the engineers, in the process recipes, in a team that has seen 10,000 failure modes and learned how to avoid almost all of them. Whoever reaches volume production first accumulates that knowledge first. And the customers who qualify their supply chains against that producer won't switch lightly, because requalifying costs time, money, and risk no chip designer wants to absorb without a very good reason. This is precisely the dynamic that made TSMC nearly untouchable. TSMC didn't win because it had permanently better equipment than everyone else. It won because it reached volume first, learned faster than anyone could catch up, and locked in customers whose own roadmaps became dependent on its process generations. Competitors have spent decades trying to close that gap. China studied that exact dynamic and is now trying to recreate the conditions that created it. In a part of the market the rest of the industry wasn't defending. Here's what makes this different from earlier chapters in the chip story. Most technology races have a catch-up mechanism. A competitor falls behind, studies the leader, and slowly closes the gap. Painful and expensive, but possible. That's how memory and logic leadership has shifted between countries before. Glass substrates may not work that way, because the advantage being built isn't just a technology lead, it's a compounding knowledge lead. The moment any company reaches volume production, every substrate that runs through the line teaches the process something. Every failure mode solved becomes institutional knowledge that can't simply be bought or copied. The customer who qualifies against that line builds their next chip generation around its specifications, and at that point switching stops being a purchasing decision and becomes a full product redesign. That's not a supply relationship, it's a dependency, the kind that can define an industry for decades. That's exactly why the biggest names in the field, Intel, Samsung, TSMC, and the glass specialist Corning, are now moving on glass substrates at a pace none of them originally planned. Intel has one of the longest track records in the technology and has shifted toward licensing its know-how. Samsung is running an active pilot line. TSMC revived its glass research program. Corning is positioning to supply the raw semiconductor-grade glass itself. The technology that much of the industry once filed under someday is suddenly an urgent priority for everyone. And when you zoom all the way out, here's the real takeaway. The next era of computing may not be decided by who prints the smallest transistor. It may be decided by who owns the foundation those transistors sit on. Every AI model, every data center, every autonomous system built in the next decade will run on chips, and those chips will run on substrates. Whoever owns that foundation and locks in the customers around it holds a position that's extraordinarily hard to dislodge. That's what $1 billion in glass may have actually bought. Not just a product, a position. Here's my honest opinion, for what it's worth. What I find most striking about this story isn't the glass itself, it's the strategic lesson hiding inside it. The entire industry fixated on one highly visible part of the chip and built its whole worldview around controlling it. Meanwhile, a parallel path to more powerful computing was quietly being developed in a completely different layer, using manufacturing skills borrowed from an industry, display screens, that nobody was watching. The decisive move in a technology race is so often not the thing everyone is staring at. I think the hierarchy of the chip industry is going to get reshuffled more than most people expect over the next few years, and the substrate layer is a big reason why. The lead that exists today is real, but it is absolutely not locked in. This is still an open race, and whoever takes it most seriously right now is the one who will shape how it plays out. Here's the question I genuinely want your take on, and be honest, because people get heated about this one. Is it a good thing when one country pulls ahead in a technology this foundational? Because competition drives faster innovation, or does the world work better when no single place controls the infrastructure everything else depends on? There are real arguments on both sides. Where do you land? Tell me in the comments. If you enjoy these deep dives that get underneath the headlines and explain what's really happening before the rest of the world catches on, subscribe to Eastern Engine and turn on notifications. We break down the materials, the supply chains, and the strategic moves that decide who leads the next decade of technology, and there's a lot more coming. Thanks for watching. I'll see you in the next one. It is the largest power station ever built. A wall of concrete stretching more than 2 kilometers across the Yangtze River, holding back a reservoir that runs for hundreds of kilometers behind it. It can generate more electricity than any other single structure on Earth, and its construction required relocating well over 1 million people. The Three Gorges Dam is, by almost any measure, one of the most ambitious engineering projects in human history. But for years, it has also been the subject of persistent questions about the quality of its construction, about its effect on the region's environment, about sediment piling up behind it, and about whether the enormous benefits it provides come with risks that have never been fully accounted for. Critics have even given it a nickname that is stuck, a tofu dread project, a Chinese phrase used for construction work that looks solid on the surface but is allegedly poorly built underneath. So how much of this is genuine concern, and how much is exaggeration? Today we are going to walk through the real debate around the Three Gorges Dam, the documented concerns, the official responses, what has been verified, and what hasn't. Because the truth here is more complicated and more interesting than either side usually admits. Let's start with the scale of what we're actually talking about. The Three Gorges Dam sits on the Yangtze, China's longest river and one of the largest in the world. Construction officially began in 1994, and the project came online in stages over the following years, with full power generation reached around 2012. The total cost is generally estimated in the range of tens of billions of dollars, with figures around the 28 to 32 billion mark commonly cited. The dam was built with three primary goals. The first was flood control. The Yangtze has a long and devastating history of flooding, with major floods in the 20th century alone killing enormous numbers of people. The dam's reservoir was designed to absorb floodwaters and release them in a controlled way, protecting cities downstream. The second goal was power generation. The dam's turbines produce a massive amount of clean electricity, displacing what would otherwise be generated by burning coal. And the third was improved navigation, allowing larger ships to travel further up the river through a system of locks. On those headline goals, the dam has delivered real results. It generates an enormous quantity of carbon-free electricity every year, and it has been credited with moderating several flood events on the Yangtze. These are genuine achievements that any fair assessment has to acknowledge. But the scale that makes the dam impressive is also exactly what makes its critics nervous. When a structure is this large and holds back this much water, the consequences of anything going wrong are correspondingly enormous. And that is where the controversy begins. The most attention-grabbing criticism of the dam concerns the quality of its concrete. During construction, the project poured concrete at a record-setting pace. In one peak year around 2000, the volume of concrete placed was several times what the famous Hoover Dam required across its entire construction. Pouring concrete that fast creates a genuine engineering challenge, because as concrete cures, it generates heat, and if that heat isn't managed carefully, the material can develop internal stresses, cracks, or voids as it expands and contracts. The Hoover Dam famously solved this problem by mixing its concrete with chilled water and running cooling pipes through the structure to control the temperature as it set. Critics of the Three Gorges project have alleged that, in the rush to set records and meet deadlines, similar temperature control measures were not applied as rigorously as they should have been, and that this led to cracking and voids in parts of the structure. These concerns are not purely the invention of outside critics. Some of the people involved in the project's own quality inspection process raised flags during construction. There are documented references to inspection teams finding surface defects, cracks, and seepage in certain areas, particularly around the ship lock system, where teams reportedly found voids in the concrete during the early 2000s. Internal correspondence from quality reviewers described the overall quality at the time using cautious, hedged language rather than glowing approval. Here is the crucial context that often gets left out, though. According to the same engineering records, those defects were identified and then remediated. Reports document that water-seeping cracks in the lock system, totaling thousands of meters in length across hundreds of instances based on mid-2000s surveys, were subsequently repaired to meet design requirements. In other words, the concerns were real, but they were also addressed through ongoing maintenance and repair, which is, to be fair, a normal part of operating any massive piece of infrastructure. So the honest picture is this. There were genuine quality concerns during construction, some raised by insiders, and there has been ongoing repair work since. Whether that represents a structure that is fundamentally sound but high maintenance, or one with deeper problems, is the heart of the dispute, and reasonable engineers have landed on different sides of it. In July 2019, a story exploded across the internet. Someone posted satellite images appearing to show the dam visibly warping and bending out of shape, sparking a wave of panic that the structure was deforming and at risk of failure. This is worth examining closely, because it became one of the most widely shared claims about the dam, and it turned out to be misleading. The apparent warping in those images was not real structural deformation. It was an artifact of how certain satellite mapping services process images, automatically stretching and distorting flat imagery to drape it over three-dimensional terrain models. When you look at a long, straight structure laid over uneven terrain in those systems, it can appear to curve even when it is perfectly straight in reality. Other satellite images of the same dam, processed differently, showed no such bending. Chinese authorities responded by stating the dam was operating normally and within its safety parameters, and independent observers who examined the imagery agreed that the viral deformation was an image processing illusion rather than evidence of a failing structure. This episode is important for two reasons. First, it shows how quickly alarming claims about the dam can spread regardless of whether they hold up. And second, it's a useful reminder to treat dramatic claims in either direction with some caution. The dam has genuine, documented issues worth discussing. The 2019 It's Bending panic was not one of them. Beyond the structure itself, Some of the most substantial debate concerns the dam's effect on the surrounding environment. And here, the science is genuinely complex and still debated. One area of concern is local climate. After the reservoir filled, the surface area of standing water in the region expanded enormously, by some estimates more than doubling. Some researchers, including geologists who have studied the area, have argued that this large new body of water altered local weather patterns, contributing to increased evaporation, shifts in temperature, and changes in rainfall in parts of the surrounding region. They point to a series of extreme weather events in nearby provinces in the years after the reservoir filled, including severe flooding in areas that had historically been prone to drought. A NASA-affiliated study using satellite data did examine the reservoir's potential influence on regional precipitation and surface temperatures, and found measurable effects on rainfall in certain areas near the reservoir. However, it's important to be precise here. Attributing specific weather disasters to the dam is scientifically difficult. The same years saw broader climate variability across China and the wider world, and separating the dam's local influence from larger regional and global climate trends is genuinely hard. So while the idea that a reservoir of this size affects its immediate microclimate is plausible and supported by some research, sweeping claims that the dam caused every flood or heat wave in the broader region go well beyond what the evidence can support. Other documented environmental concerns are more clear-cut. Sediment management is a real and ongoing engineering challenge. The Yangtze carries a heavy load of silt, and dams interrupt that natural flow, causing sediment to build up in the reservoir over time. Water quality changes in slow-moving reservoir water are a recognized issue, and there are well-studied concerns about reservoir-induced geological activity, where the immense weight of stored water and fluctuating water levels can increase the frequency of small landslides and seismic events near large reservoirs. These are not unique to the Three Gorges Dam. They are known challenges for major dams worldwide, but the sheer scale here amplifies them. One of the more thought-provoking concerns raised by critics involves not the Three Gorges Dam alone, but the entire system of dams now operating on the Upper Yangtze and its tributaries. Over the years, China has built a series of additional large hydropower stations upstream on the Jinsha River, which feeds into the Yangtze. On one level, this makes engineering sense. Upstream dams can hold back floodwater and trap sediment before it reaches the Three Gorges Reservoir, easing pressure on the main dam. But critics point out a less comfortable implication. Stringing many massive dams along the same river system creates a chain. The concern is that if any single dam in that chain were to fail catastrophically, the sudden release of its stored water could threaten the dams downstream of it in a cascading sequence. It's a low probability but high consequence scenario, and it's the kind of systemic risk that's genuinely worth engineers thinking carefully about. Not because failure is likely, but because the stakes are so high. It's worth stressing that this is a hypothetical risk, not a prediction. Modern dams are built with significant safety margins, and a cascading failure would require an extraordinary chain of events. But the more dams you build on one system, the more the individual structures become interdependent, and that interdependence is a legitimate subject for ongoing safety analysis. Part of what fuels skepticism about the dam is the series of expensive follow-on projects that have been built around it over the years. Projects that critics argue exist partly to manage problems the dam itself created. One example is the bypass system for shipping. Because traffic through the dam's locks can back up significantly, with ships sometimes waiting days to pass, authorities built an over-dam transport route. Goods are unloaded from ships on one side, trucked overland along a dedicated highway, and reloaded onto ships on the other side, bypassing the lock bottleneck. The highway portion alone reportedly cost hundreds of millions of dollars, and that's before adding the upstream and downstream port facilities. Another major project is a large water diversion tunnel, begun in 2022, designed to carry water from the Three Gorges Reservoir area through a nearly 200-kilometer tunnel to the Han River. Officially, this is framed as a follow-up to China's broader water diversion programs, aimed at maintaining water levels downstream. But analysts have noted it also serves another function, giving the dam an additional channel to discharge water during flood conditions, helping relieve the difficult balancing act the dam operators face. When a major flood hits, releasing too much water risks flooding cities downstream, while holding too much back risks flooding cities upstream. An extra outlet gives operators more flexibility in that trade-off. Supporters would frame all of this as sensible infrastructure that maximizes the value of a major asset. Critics frame it as evidence that the original project created cascading problems requiring ever more expensive fixes. Both interpretations describe the same facts, which is often how these debates work. Underlying all of these specific concerns is a deeper debate that goes back to before the dam was ever built. During the project's planning and evaluation in the late 20th century, it was not universally supported, even within China's own expert community. The environmental impact assessment process was genuinely contentious. Some experts argued that the ecological and environmental downsides of the project were serious enough to warrant reconsidering whether it should proceed at all. And there were disagreements about how the official conclusions were ultimately framed. This internal debate is part of the historical record, and it reflects something true about megaprojects everywhere. Enormous infrastructure decisions involve real trade-offs, and reasonable experts can disagree about whether the benefits justify the costs. That tension has never fully gone away. Supporters point to the clean electricity, the flood control, and the navigation improvements as transformative benefits for a country of over 1 billion people. Critics point to the displaced communities, the environmental disruption, the sediment and water quality challenges, and the ongoing maintenance burden, and argue the full costs were understated from the beginning. The most honest assessment is probably that both things are true at once. The Three Gorges Dam is a genuine engineering achievement that delivers real, measurable benefits. It is also a project with real, documented downsides and ongoing challenges that its operators have to manage continuously. Whether the balance comes out positive or negative depends heavily on which costs and benefits you weigh most heavily, and that's ultimately a question of values as much as engineering. Let's come back to the question in the title. Is the Three Gorges Dam facing a new crisis? The responsible answer is, not in the dramatic, imminent collapse sense that sometimes circulates online. The dam has now operated for roughly 2 decades. It has weathered major floods. The viral claims about it physically bending were debunked. There is no credible evidence that the structure is on the verge of failure. What the dam does face is a set of ongoing chronic challenges that don't make for dramatic headlines, but are genuinely significant. Sediment accumulation that worsens over time, environmental effects on the surrounding region, the maintenance burden of a structure built at record-breaking speed, and the systemic questions raised by an entire chain of dams on one river system. These are real engineering and environmental issues that will require attention for as long as the dam exists. So rather than a single sudden crisis, the more accurate picture is a massive piece of infrastructure that delivers enormous benefits while carrying a long tail of complicated, slow-moving problems. Exactly the kind of trade-off that comes with building at this scale. What do you think? Do the flood control and clean energy benefits justify the environmental and engineering trade-offs? Or do you think projects on this scale create more problems than they solve? Let me know your honest take in the comments. This is one of those topics where thoughtful people genuinely land on different sides. And if you found this balanced breakdown useful, consider subscribing so you don't miss the next deep dive into the engineering megaprojects shaping our world. For decades, 3 companies have controlled almost the entire global market for computer memory: Samsung, SK Hynix, and Micron. Their chips sit inside smartphones, laptops, gaming computers, servers, and artificial intelligence data centers. Now, a Chinese manufacturer founded only 10 years ago is preparing an expansion that could change that balance. Changxin Memory Technologies, better known as CXMT, is expected to add roughly 85,000 wafer starts per month of new DRAM manufacturing capacity during 2026. Samsung is expected to add around 15,000. That means CXMT could install more than 5 times as much new wafer capacity as Samsung this year, not 5 times as much total production. Samsung remains far larger, but in terms of new capacity being added during 2026, China's leading DRAM producer is moving faster, and CXMT is preparing to raise another 29.5 billion yuan, approximately $4.3 billion, through one of the largest technology IPOs ever attempted on Shanghai's STAR market. The money is expected to support production expansion, research, and the development of more advanced DRAM, including memory designed for artificial intelligence. This is arriving at an extraordinary moment. AI data centers are consuming memory faster than manufacturers can comfortably supply it. Memory prices have risen. Samsung, SK Hynix, and Micron are earning enormous profits, and CXMT's revenue reportedly increased more than 7-fold in the first quarter of 2026. But rapid expansion does not automatically make CXMT a technological equal to Samsung. The Chinese company is still behind in advanced high-bandwidth memory. Its manufacturing efficiency, product mix, and total output remain smaller, and increasing wafer capacity during a memory shortage can be highly profitable, or extremely dangerous if demand weakens before the new factories are ready. So is CXMT becoming a genuine 4th global memory giant? Or is it expanding at the most expensive point in a historically unstable industry? Why memory has become the new AI bottleneck? When people discuss artificial intelligence, most attention goes to processors. NVIDIA GPUs, custom accelerators, massive clusters filled with computing power. But a processor is useful only when it can receive data quickly enough. Every AI accelerator needs memory to hold model weights, temporary calculations, instructions, and the information moving between layers of a neural network. If memory cannot deliver that data fast enough, the expensive processor waits. That waiting time is one reason memory bandwidth has become so important. Traditional DRAM serves as the working memory inside computers. It stores information that processors need immediately. Unlike an SSD, DRAM is extremely fast, but it loses its contents when power is removed. A modern server may contain hundreds of gigabytes or several terabytes of DRAM. An AI cluster can contain thousands of servers. Multiply that memory across an entire data center, and demand becomes enormous. AI is also increasing demand for a specialized form of DRAM called high bandwidth memory, or HBM. HBM stacks multiple memory dies vertically and places them close to an AI processor. Thousands of tiny connections move data between the layers and the processor at extremely high speed. But HBM is difficult to manufacture. It requires advanced DRAM dies, precise stacking, specialized packaging, and strong control over heat and yield. Producing more HBM can also consume manufacturing capacity that could otherwise make conventional server, smartphone, or computer memory. This creates pressure across the entire market. As the established manufacturers redirect advanced production toward profitable AI products, supplies of standard DRAM can tighten. That is the opening CXMT is trying to exploit. The Chinese company that appeared almost from nowhere. CXMT was established in 2016. That makes it extremely young compared with its major competitors. Samsung has manufactured semiconductors for decades. SK Hynix traces its history through several older Korean memory companies. Micron was founded in the 1970s. DRAM is one of the hardest semiconductor markets to enter. Each memory cell must store a reliable electrical charge while occupying as little silicon as possible.